running through a few of our projects in terms of adaptability. We'll be going sort of at the bottom and working our way back to the top. Along with me is Zenon Radowich, another principal in the firm. He'll be talking more about the innovation piece. So let's jump right into it. So I'd like starting off with this slide. This really represents for us the work we've done over the last 20 years in terms of adaptability in retrofitting and recladding projects. And we saw this 3 years ago at the Munich trade show. And this is a great metaphor for what we think is the balance between design and technical approaches in reclad projects. So yes, this is an active glass seesaw and structurally engineered. So we're going to run through a few projects to begin with, and then I'll hand it over to Zenon. Traveling back 10 years ago, we worked on 2 projects. These photos on the left is Nova Scotia Power, circa 1950s, and on the right is 222 Jarvis in downtown Toronto, which I suspect a number of you are familiar with. That's an original building photo. Starting with Nova Scotia Power in Halifax, we were engaged to retrofit a 1910 and subsequent additions to the project, essentially a concrete bunker that was an active power station, and convert it to their new headquarters. So we completed the project in around 2012. That became the first LEED Platinum project in the Maritimes. We applied innovations from LEED, such as chilled beams and seawater cooling. And this is some of the end product photos where we kept the existing steel, reintroduced glazing in the concrete shell facade. And this is an image of what we were dealing with. So we cut openings, applied structure to introduce new glazing, and cut holes wherever we needed to. So lots of robust existing infrastructure that we adapted to, and in the end, we were able to achieve what we think is an amazing product along the harborfront in Halifax. Jumping ahead to 222 Jarvis, very brutalistic building that was Sears head office at the time. Infrastructure Ontario purchased it and labeled it as their marquee project in terms of rehabilitation. At the beginning of the project, it wasn't really labeled for any kind of sustainability, but as we progressed through the design, we introduced LEED aspects and were able to achieve LEED Gold. So here, the message was really about how to introduce an entrance, adapt a facade. We redid all the windows, looked at energy performance through the facade that was there, and really in the end, we looked at introducing new daylighting through the center core, and the highlight of the project was certainly the front entrance. And here we did a marquee entryway canopy and really adapted to the existing framing of the building. So jumping ahead, this goes back about 6 years now, where we looked at 120, 130, which are the middle building and the building to the left. 100 Adelaide was just completed as a brand new tower, which also adapted to the existing heritage facade on the right. So these buildings are just a couple of blocks away. Certainly, I'm sure a lot of you have seen the new product opened up now. And as we were working through that process, these were existing original WZMH buildings back in the 70s. We looked at the existing framing. I think as I speak, we know that the number of projects we've touched on existing buildings, the infrastructure is robust. The existing curtain wall framings built back in the 70s were done very well, and certainly adaptability to them was quite easy. So we looked at different methods. Certainly there was failure in some areas, but overall the mullions were kept, and we adapted a cassette frame type of approach to achieve a new facade, vision glass, and spandrel. So here on the right, it was the image on 100 Adelaide, the new tower. In the middle, 120, existing tower, and on the left, 130. In the end, with the new facade system, we created this family of buildings, each having different glass types, but also had some similarities to them. So moving forward, we continue to work on these type of projects, and we really are addressing immediate concerns, failures, and we adapt a new storyline to them in terms of design. So here's 330, just again, couple blocks away, 330 Bay. And 76 Adelaide, which you'll see, again, another block away, is a new facade going up, floor-to-floor glass. We stripped out the old failing facade and introduced new steel structures along the edge of slab, adapted new framing that created the fireproofing, and as well supported these new floor-to-floor bent glass plates. Again, there's a storyline approach, there's technicality adapted into it, and we were able to achieve these designs. Moving even further, what we'd like to touch on is just adaptability of innovations. All the projects I've just mentioned before, as much as some of them were LEED and some of them were sustainable, they really haven't touched and got into the conversation about net zero, which is really the message today overall. So again, back to some of our travels we did overseas, we were looking at some of these mullion frames that have, the gasket is completely sealed, and really talk to a very, very high performing type of a facade. And as well, we're looking at products that are speaking to R10 type values, vacuum insulated glass. I'm sure some of you have heard about this product. It is out there on the market. We are investigating it. There's no reason why we can't adapt some of these products now with the engineering and some of the earlier conversations you've heard today about how high-performing products can be introduced into our designs. So here you can see that we can easily achieve R10 in a curtain wall. So that's the message we want to take away today. The first part is really to demonstrate our stock of projects that really address existing buildings, and we know that there's a surge in introducing new facades into old buildings that are either failing or require rehabilitation. So without further ado, I'll hand it over to Zenon.
So, thanks, Harrison. So I'm going to talk a bit about what we're doing in our lab. In 2017, WZMH started an R&D lab with a focus very much on the IoT world, Internet of Things, but also looking at how to make buildings smart, how to make buildings more sustainable, how to make buildings more energy efficient, and again, really driving the whole net zero, zero carbon thing. So a lot of what we do in our lab is we play a lot, where we come up with concepts. We don't necessarily take these concepts and kind of put them into our buildings yet. It's very much forward-thinking ideas that are maybe 4, 5, 10 years out. Some of our ideas we're actually implementing now, and some of our ideas actually go beyond actually just building architecture. They get into actually electronics and devices and controllers, where we partner with companies that specialize in those devices. So how do you move forward on this thing? The green. So this is a study we've been doing for the last couple of years and playing with the whole idea of solar, whether it be solar tied into the building envelope or actually solar inside the building. So we've looked at bifacial panels, where we actually have solar films on both sides of the panels, and we're doing studies where we're actually putting these films or solar panels on the upper portion of interior glazed units to basically capture the natural daylight that enters the building that reflects off of white surfaces. And also just the light that we get from the light itself from the ceilings, artificial light. So a lot of studies that we've actually done, we can prove that we could capture a lot of this bouncing light and artificial light from panels that are actually facing the inside of the space and use that to basically power up things like lights and stuff like that. So these are the kind of mock-ups that we've done, and working with actually solar films. So there's these great solar organic films that are being produced by many companies. Very easy to install, laminate, whether you put it on glass or walls or ceilings or whatever. The idea is to kind of look at the advantages of, again, capturing artificial light within spaces and the natural light that bounces off from the exterior, bouncing off of horizontal and vertical spaces inside the building. Just some images of these actual films that we place. And so we monitor these films. We install them on glass. We take readings, measurements, and actually even hook up devices to them and see how they perform. And this is a simple little study where, on the south elevation of this building, using a combination of exterior bifacial PV panels that capture both natural and artificial light, we could actually power up a portion of the building. The portion on the right-hand side of this slide here, the interior, that actually goes beyond the building envelope, and that's where we're actually capturing energy from artificial lighting throughout the space inside the building by placing solar films on desks in different locations. within the actual space to actually capture that artificial light, and then basically charge things like phones and tablets and stuff like that. So a lot of opportunities to really kind of drive building performance from an energy perspective by capturing both artificial and natural daylight. This is, a mock-up that we're building and working on. We're actually looking at, sloping the actual called curtain wall. So, a lot of the buildings that we design and build, the curtain wall is a rectangular shape that's basically fully 90 degrees, but doing simple things to it and giving it a bit of a tilt, and then introducing a solar panel, you could actually, improve the performance of that panel because it has a bit of that angle. So, an opportunity to kind of look at how we build buildings and introducing this, called angled piece that could then be scalloped as the building goes up to capture that natural light in a better way. This is actually a product that we developed. It was the first thing that we invented in our lab in 2017. We call it the Intelligent Structural Panel. So it's an actual floor panel, that white component you see there that has that kink. That's the actual structural floor slab. It's roughly 2 inches thick, and it carries the same loads as basically a residential building or hospital building. We did not develop the structural component. It was already developed by another company. We simply developed the concept for inserting an intelligent layer in that floor. So it's a modular product that as you build your building and install these floor panels, you're installing also a good component of the technology within the actual building. So the technology to basically power your lights, all of those things. But now we're looking at it and how we integrate it into the building envelope and how we integrate it with the curtain wall, how we tie in solar to the actual floor panel itself and run that green energy that we generate from that solar panel directly into the actual floor assembly and then feed those devices that basically require that power, DC power to DC power. This is a concept drawing. Just to let you guys know that this panel itself is going to be installed in the first building in Toronto at a university, a small little building. It's currently in design right now, slated for construction within the next year, year and a half. So hopefully we'll be walking on it within the next 2 years. So this is kind of a section kind of showing just how thin that panel actually is compared to, 8 inches of concrete or steel decking concrete, very, very thin. And then kind of how it interacts with the exterior envelope. And the next concept we're kind of working on is actually looking at how we prefabricate not only the floor, but the actual called building envelope in these called L sections that would be 10 feet wide. So you can imagine building this building and installing a portion of the floor with the actual envelope as one piece. So kind of really pushing the envelope on modular prefabrication for commercial buildings, not so much for residential, but for commercial buildings, high-rise buildings where you're installing floors and walls at the same time. This is a study we just recently completed. We kind of believe that the industry is kind of pushing a lot of insulation and saying that we need to add a lot of insulation to our buildings to improve the energy performance. We're kind of thinking that's not necessarily the case. We're big believers in designing buildings that have very good high-performing air barriers, but also looking at maybe alternative materials for insulation. So we did these studies where we built these boxes out of traditional insulation solutions, good air barriers, but also looking at alternative insulation products. And we're testing these assemblies in terms of how well they perform. And actually, the results are pretty interesting, where some of them show that these, highly or heavily insulated boxes with kind of a quasi-performing air barrier only perform slightly better than those boxes that have half as much insulation with a very good air barrier. But also we're looking at other things too and introducing different materials within the actual called insulation makeup. So combining a bit of traditional insulation with heat-reflective fabrics or different materials that actually reflect that heat. And we're seeing a huge performance increase in those little mock-ups that we're actually building. So, our conclusion is, let's not maybe look at making our walls thicker with a lot of insulation, but maybe looking at how we build our walls with very good quality air barriers, but also looking at alternative insulating materials to basically really improve the performance and reduce the overall thickness, and therefore also reduce the amount of materials you need to build these assemblies. So very excited about this stuff. Again, it's all happening in our lab. We build these mock-ups, we install the heaters, we install microcontrollers, thermostats, and basically measure all of this stuff. So fun stuff that we're doing. This is kind of a concept that we were playing with, the idea of basically creating an energy-producing curtain wall. So, I think all of us have worked on buildings where we understand how wind patterns flow around buildings. So this concept is installing simple little fans as part of the actual curtain wall assembly, the building envelope assembly, and looking at how much power we could generate from those fans that are basically turning as the air kind of flows up and around buildings. So, early studies show that there's an opportunity to kind of generate a significant amount of energy, but it really depends on the location of the building, the wind patterns, how tall the building is, all that kind of stuff. But again, ideas for really looking at making these buildings, more than just, or the cladding, more than just the cladding, but actually something that actually produces energy, whether it be a combination of, solar films and BIPV, or things like this where you take advantage of how wind flows around buildings to turn little turbines to basically provide power. And that's basically it.
Where's it mouse?
Oh, okay. Yeah. Hi. We were using that extra time that they gave us because they finished short to have a little bit of an IT problem. So, great presentation, guys. Really fantastic. I really kind of appreciate the kind of levels of research and development that you're actually bringing to your practice, and it's really nice to see kind of enhanced thoughts towards prefabrication, where you can actually start to reduce the amount of waste in the construction process. So fantastic. That's great. So next up, we have John Kraus he's president and CEO of Boston Valley Terracotta. Welcome.
Thank you. Yeah. Can everybody hear me okay? Is that too loud? I want to, okay. Hold on, let's switch them on. Hello, testing. Can you hear me okay? No. I got to put it up a little higher. Okay. How's that? Better? Okay, thanks. I'm excited to be here. I want to thank Zach World of Facades for allowing us to talk a little bit about terracotta. Obviously, it's a very flexible material, and our goal is to see it on as many buildings as we can, I guess, because it's so beautiful. And I'm going to feature some really powerful examples of how it can be used not only in historic preservation, but also in new construction. So this opening slide, we're involved with Building E up at the well. I'm sure everybody is aware of the size of that construction project going on currently in Toronto. It's going to be a fabulous building when it's done. And we had a lot of interesting dynamics involved with the design-build process that I'll share with you. Okay, so just a little history about the material. Architectural ceramics goes back in history well over 3,000 years when people discovered soft clay and fired it in wood firings. They realized that you could shape it and mold it in a number of different configurations, and it's very durable. It's been used here in North America for well over 150 years, so it's got a proven track record. And the beauty of the material is it's very plastic and soft, and it can be formed as a hollow extrusion or very thin type of veneer product, which works very well on contemporary architecture, along with providing replacement blocks for the historic terracotta, which is what our company does. We provide both. A little bit of history about a current event that happened during 9/11. The building on the left, 90 West Street, actually took a severe blow from the World Trade Tower incident, and that building remained on fire for 6 days before the fire department could come to it and actually put the fire out. It's one of the only buildings in the area that's remained standing because of the durability of the ceramics and the fireproof nature of the material. On the photo to the right, that is the Guarantee Building from Louis Sullivan, who was basically the genius that really exploited the material to its fullest extent by being able to model it in a very ornate fashion, but using it as a lightweight ceramic module on the skyscraper buildings that were developed in Chicago. So there's 3 points that we like to talk about when we work with this material today, especially in architecture. We want to be green as much as possible, so we recycle all our content because there's a lot of embodied energy in the scrap that gets cut off the material. So now we have the ability to actually grind the scrap up and then sort the particle size and recycle it back into the mix design. So it's fully 100% recyclable material, and it's a lot of tied up carbon in that product that's actually getting reused back in the material. So it makes it a wonderful, sustainable building product. Some of the examples that we've worked on in my career over the 35 years that I've been doing this type of fabrication in ceramics is partnering up with the local contractors, curtain wall manufacturers, and architects and facade engineers to help fix these old buildings, because we like to think that some of the greenest buildings out there are actually the ones that are already built, and how can we preserve them and keep them viable for the future. It's not a very big envelope, but it was a very important piece of architecture here in Toronto to save this facade and get another 100 years out of it with very little maintenance. On closer inspection, when we got up to the material, we realized that there were fiberglass replacements that were done about 20 years earlier that have actually failed because you couldn't get mortar to bond to it, and the material actually started to fade and crack from the UV. So the design team made an executive decision to actually remove the fiberglass and go back to the historic terracotta replacement material to actually bring the former beauty of the facade back. So that's just a little illustration of the contractor removing the samples to send up to our facility. But nowadays we have the ability to actually scan this ornament right in situ without even having to take the fragments off the building, which is a little bit less of a carbon footprint to extract a historic sample, put it in a box, and ship it all the way down to our factory outside of Buffalo. Now we can actually scan the ornament in place and fabricate, do the shop tickets and fabricate it without the extraction. So we're really excited about that technological advancement. Obviously, when you're working with this material, you have an abundant choices of glazed surfaces that are available on the ceramic that you really can't achieve that look with any other material. That's what makes it so unique. In today's contemporary architecture, architects are really exploring beautiful finishes to make their building really stand out and be a signature piece. So we bring to the table well over 40 years of experience at not only glaze formulation, but the ability to deliver a unique finish onto the ceramic without adding very much cost to the additional bottom line. Also, I'd like to note that within that glaze formulation, we're featuring recycled glass from Vitro, which is a borosilicate glass, so we're being as green as possible by taking that recycled glass and using it in our formulation. So you get kind of a double whammy when it comes to LEED points for that type of recycling. Another beautiful project that I worked on personally with Hamid, and we had a great experience on this, was on 1 King Street, where there was, the building needed a repair, and it's an absolutely excellent example of historic terracotta used up here in Toronto, and how well the material withstood the test of time with very little maintenance on it. So it was exciting to see them not want to tear the building down, which also is a tribute to low carbon footprint and being as green as possible. A lot of you are probably may or may not be familiar with the building, but I urge you to walk by it if you have any time during the rest of the week to take a close look at it. But it was masterfully restored. Again, we worked with WSP, with Hamid personally, on this job to be as sensitive as possible to the existing historic fabric and only replace the elements that were severely damaged. We like to think that we were the first manufacturer here in Canada that produced the very first contemporary rain screen up at Vaughan. I worked with Victor, who's out there with Triumph, and we were chatting about that a little earlier. There was a lot of challenges when we started this project. It was an absolute masterpiece of a building by KPMB architects, and working with that team was a lot of fun, and we learned a lot about modern rain screen while we were doing the project. At the time we did the project with Ritz Metals, it was considered a stick-built system, but what made this building exciting is not only did it feature wall panels, but there was a series of louvers that were 12 inches deep that had to be supported on a unitized curtain wall, and it was some very early examples of how you can actually work with this material to control sun shading. And to this day, architects are still trying to understand and work with this material in a fashion that can employ this type of louvered baguette system to actually control heat gain in the curtain wall. And being the fact that it's fired ceramic, it has such a durability, it'll never warp over time or fade from the UV, so it makes an excellent choice for your louvered systems. The color was custom selected. It's a natural through body color, and part of the beauty of working with the material is it's not all exactly the same finish. You do get subtle shade variation within the facade, which makes it even more of a crafted look. And I think that's the kind of look that a lot of the architects today are looking for, is the natural range of the material. And on the left, you can see the illustration of the cross-section of the wall that was used. We manufacture not only the ceramic panel, but we provide the aluminum backup structure, the clips, and the engineering and all the drawing layouts to actually be able to execute this project. So you get a lot of help in working when you work with our company. But the beauty of the system is it is a rain screen, and the Canadian government had instituted rules way ahead of the American architects that are designing. So you guys had a big jump on how to design and build with this product before we did down in the States. So we actually learned a lot working with the design team on this project on how the entire wall behaves and just the beauty of the rain screen system itself. The last project I want to talk about is the well, and it's building E, and you can see on the right-hand side is where the actual ceramic material is being installed in a rain screen fashion. I think one of the things that also ticks some lead points in the sustainability with this project is the proximity from the clay pit to the delivery to the job site is well within a 500-mile radius. So when we're trying to talk about being as green as possible and reduce carbon footprint, it's nice when you can partner up with teams that manufacture within a regional area and can deliver it to reduce the amount of carbon that's required to extract the material and actually fabricate it. So that made it actually extra special for us, knowing that it was right up here in Toronto. And working with the design team with Adamson and BPD and the other groups involved was a fun experience. We did go through a little design, build, design, assist with some of these shapes. The beauty with working with the material, it's hollow and lightweight, and we can fashion it in a multitude of custom configurations. And there's still a lot of realization in the future to understand how we can start tapping into that hollow void space of the ceramic and actually move that air around to make the performance of the building maybe even cooler and less energy intensive. We're developing some research in our own ACAW event that explores those concepts. And there's some books out on our display table if anybody's interested to thumb through it. But there's really a lot of things about working with this material that can be employed to make a building even more green and perform to a higher performance than just putting a fancy ceramic piece on the wall. When you see the building at night, it's going to be lit up. I don't know when it's scheduled to be complete. We're anxious to get down there and take a close look at it, but it's absolutely a stunning piece of architecture, and the entire complex is really just going to be a great addition to the city. So these are some of the layout drawings that we provided in working with Clifford Masonry, who we've had a long-standing relationship in the restoration business. And working with that team, we were able to develop the, not only the mock-ups that were required for the project, but also the training that was necessary to make sure that the contractor was comfortable in how the material is actually installed on the track and clip system. Every panel has a unique position on the facade because the architect was really looking for a very crafted finish. He was not interested in a monolithic color, so they personally selected 3 shades of white to give it that really handmade, more of a historic kind of finish that kind of ties into the beauty of the surrounding neighborhood. And I think they did a terrific job of actually selecting those colors. I know white, you know, there's thousands of shades of white in glaze, so you can agonize over that as an architect, but it really is worth the added effort to put into it when you're selecting the finish on the building, because once it's on there, you're pretty much stuck with it. So there was probably about 8 to 10 months of submittals of literally hundreds and hundreds of shades of white for the architect to look through before they narrowed it down to the 3 shades. So every piece was unique. It had a very specific location it had to go to on the facade based on that color scheme. And we were able to work hand in hand with the design team and the contractor to make sure that we were able to organize the drawings in a fashion that they were able to set the stone in the exact place. This is a section cut through one of the columns. In this particular iteration, you can see that the unit was actually designed as 2 pieces, but in further conversation with the architect, they really weren't going to be excited about showing an open joint on the nose of that profile, so we were successful at actually manufacturing that piece as one big, large extrusion to accommodate the design intent. So there were a lot of back and forth iterations with how to carve up the overall facade into a jointing scheme that worked for both the architect and the manufacturer to be able to deliver the design intent as close to the original proposal. These were some of the mock-ups that were developed. The mock-ups at the job site were much larger. We weren't able to come up and witness any of the testing because of the COVID scenario that was happening over the last 2 years. But we mocked up a smaller version of it at our facility. It's really hard to understand the scale of the material unless you're standing next to it. So if you were actually able to stand next to that unit, my head would come up to about here, you know, so it's quite a massive extrusion, but it was all able to be hung on our existing track and clip system without any issues in the engineering of the support. A lot of the pieces had to be custom water jet cut that went around that curve, and the actual bullnose piece that splits off of that column were hydraulically pressed. So there were 3 forming methods that were utilized at our facility to actually execute all those shapes. And then, of course, the beautiful canopy that is connecting the 2 buildings together will be just another stunning piece of architecture. And as you can see, the installation is about 50% complete, I believe, at the job site. So I think anticipated opening will probably be sometime next year. Some of the green energy solutions associated with ceramics is the fact that it has a low embodied energy in the manufacturing process, which makes it attractive when you're designing with a facade and you're looking to get a low carbon footprint. We actually tick some of those boxes. It's a very malleable and soft material. You can see how plastic it is in the hands of the crafts person. You can actually hand press with it. You can slip cast with the mix. You can extrude it, and you can hydraulically press it. So it's got this wonderful ability to be flexible, thin, hollow, fireproof, and have a low carbon footprint because of the fact that it doesn't require a lot of energy to harvest it out of the ground, manufacture it, and deliver it to the site. We have our own little research wing that we conduct at our facility. It's referred to as the ACAW event. That's a shot working hand in hand at the research facility that we are allowed to use up at the University of Buffalo School of Architecture and Planning. And the only thing that really makes this work is the AE community. It's a personal invite. If anybody is interested in signing up for ACAW, we'd love to talk about it with you. But it's really an area where an architect can explore how to design with the material, possibly on an idea that he has for a client, or his own personal research of where he thinks that you can get better building performance in working with the material. So what we do is we partner up with the architect. We run a design charrette that lasts about 3 months, and then we have about 4 months to make all the product, and then they come into Buffalo, and we house them up at the University of Buffalo on campus, and we spend a whole week putting the assembly together. The event has grown over the last 7 years. We've partnered up with some major glass manufacturers and curtain wall contractors and other associated metal folks that can provide all the necessary hardware to build more complex assemblies, but it's purely based on research. It's held in an academic setting, and there's always universities like Ryerson was involved a couple of years ago, and schools like that local to the area that want to be part of this as an educational exercise as well. Getting back to the food pyramid, I think some of you are very familiar with this, but our material sits somewhere in the middle of this area, where it kind of just gives you a quick illustration of at the top of the pyramid is where the most energy goes into making the product, and at the bottom is the most sustainable and least energy intensive. Of course, you see wood and gypsum and things like that, and hay and straw and other renewable product. But over on the right, terracotta is the next level up because you have to fire it in a kiln. It requires a little bit more energy. And this is just kind of a quick overview. I was very nervous about showing the slide. I've double checked my facts. I've had a couple PhD guys that we work with at the CACT down at Alfred University, who are a part of our QA/QC wing. Dr. Carty also reassured me that this is a very accurate diagram of how much energy is actually required to go into all those raw materials. So you can see when you're specifying things like clay, terracotta, brick, tile, they have some of the lowest embodied energy in them because of the ease of the extraction and the processing from proximity to pit to the factory. And just to recap, again, I think the greenest building out there is the one that you restored because it requires possibly the least amount of intensive invasiveness and product that's going to be required to refurbish it. So we're always promoting the sustainability of the existing building and the heritage that goes along with that building in the community, and we're proud of that. And of course, our groundbreaking moment here in the Toronto area was to partner up with the design team and actually bring Vaughan City Hall to life using ceramics here in Toronto. And then, of course, the Well, which is one of the largest ceramic rain screens, I believe, in North America, that is currently under construction. So it's really kind of an exciting moment for Toronto because you guys have such beautiful architecture here and such a great mix of buildings, and I think this is an excellent example of what's going on in your city. So with that being said, I just want to close out the program and say thank you.
Thanks, John. One element you didn't actually mention about your product, John, was the fact that it ties into design for disassembly really well. So you can actually reuse the material in a circular economy that we're actually going to have to start to really impose on our structures and buildings. So that's great. So up next is our third John of the day, John Koymans from RJC. He's principal there at RJC. Thanks.
Thank you very much. Sounds like my mic's working. That's great. It's a pleasure and honor to be here today presenting to you. Facade engineering can mean a lot to a lot of different things to a lot of different people. At RJC, it is more than just building physics or sustainable aspects of the envelope. It is a holistic design approach that encompasses the performance of the envelope system, the structural integrity of the envelope system, and the contribution to its environment. So for my talk today, I'm going to take you on a journey of my professional life and how I personally got here today. And as you can see, I've been in the business for quite some time now, and my passions have evolved as my career continued. I will briefly chat about my early interest as a structural engineer and show how different opportunities challenged and excited me, shaping what my beliefs are as a design consultant and what is important to me and RJC going forward. From structural engineering of buildings to structural glass engineering to facade engineering, and then climate change, and how we need to all do our part to help our planet. So just some early interests in what I was working on in my early career as a structural engineer, mostly in retail and cultural buildings. You can see some of the buildings here. Top left is the Agacon building in Ottawa, and then the next one is the Four Seasons Center here in Toronto. A lot of major mall expansions, Yorkdale, the Core in Calgary, Halifax Shopping Center, Square One, etc. Leslie Dan Pharmacy building here in Toronto, which many of you may know about, and MGM Crystals in Las Vegas, another challenging retail project. That's basically a lot of the interest in my early days as an engineer. Then I got into glass structures, and in many projects you just saw on the previous slide, you will see a lot of structural glass assemblies. North America was being introduced to many new and exciting options of glass as a structural element. All of this was possible and on display throughout Europe and Asia, so why not here? The main reason is that structural glass engineering is not taught in North America, at least not in the early 2000s for sure, or before. I got lucky and met up with a colleague in Germany who is now a good friend of mine, and he's recognized as a structural glass expert in Europe, and took the time to train and educate me on all the intricacies of structural glass engineering. Over the past 2 decades, there has been a concentrated effort in advancing the North American structural glass codes and design standards, all influenced by our friends over the pond. For me, it all started with the Four Seasons Center for the Performing Arts. The unique way that we use glass in the exterior walls of the city room, as well as the feature glass staircase that links the mezzanine floors together. In this particular case, we used horizontal glass girts instead of the traditional vertical glass fins for something a little bit different and unique. And the glass stair itself is truly a structural glass staircase with no steel other than clamping the individual elements together to create a longer glass beam. So the balustrades themselves act as the glass structure itself, carrying all the load spanning from floor to floor. And the glass treads and risers create the U-shape and stability for that balustrade system. The critical design features that were needed to design the control at the consultant level. As it says in the caption below, I have not looked back since with many exciting projects throughout North America, some as a design consultant and some as engineer of record to a specialty glazing manufacturer. So in many instances here, we have the skylight at the Core again, we have a glass bridge at the Ritz-Carlton here in Toronto, Top right is the observation deck at the Sears Tower in Chicago. You've seen some pictures now of the well. That's the middle left. That's our canopy design that's being constructed right now on site. Bottom left was a very interesting one, which was a glass living room in California, where all the glass elements are load-bearing and also glass shear walls in a high seismic zone. So you can do anything with this material if you just have the vision and the engineering for it. So no matter what the use is, structural glass design should include a design consultant, in my humble opinion, especially the most prominent and unique ones. Designs that require some basis of engineering and detail to help ensure the intent is maintained and to ensure the structure actually works. An engineered solution so that the tendering process is cleaner and results in less surprises once awarded. Projects like the glass dome at the Erin Mills Town Centre, where we utilize double curved laminated glass, or the bridge at the Ritz-Carlton here in Toronto, where all the connections, details, and glass sizes were engineered and detailed to ensure the vision was maintained throughout the process. Expanding on the why, have a consultant on board. For those who have seen me present before, many of you may have seen this slide as well. It is the basis of all we do in our structural glass design team. All of these elements are very important in a structural glass design. The ones in blue are what we take extremely seriously because it tells you whether the design is going to work or not. You have the connection types, obviously are very paramount and important in glass design, but redundancy, post-breakage, how you can construct it, and how can you actually disassemble something to replace broken pieces. All of these things need to be taken into consideration when designing a glass structure and are very important. And why we end up getting involved is at the bottom there, is to protect the design, and that's the important aspect of it. Just structural glass was not enough. Just steel was not enough. The training and design progression continued into other materials and how they relate to glass systems, both as a material option and for a detailing necessity. All components of the glazing system require a deeper dive into how they are detailed together in order to achieve the desired aesthetic of the elements. Connections and compatibility are key metrics in a successful design. Understanding these issues is key for the consultant in order to achieve the desired results, to create a competitive tender, and to protect the design going forward. It is critical that the consultant is able to speak to the design at all levels so that the intent is maintained without sacrificing the design itself. So what is next in the evolution of this design feature? Expanding the design to include all aspects of the enclosure, not just the structural aspects of it. And once again, looking to Europe to see what advancements have been made and how they handle enclosure design. So facade engineering was the next natural progression. And based on what you have heard and seen so far here today, I think it's clear that I am not a building envelope expert. But I am driven by a passion to provide a better service for our clients. Nobody needs to be an expert in everything. They just need to assemble the right team to address all the issues. We need to look at the whole system. We need experts to look at each component of the design in a team setting. This ensures that what is being envisioned is possible. It adds a fresh set of eyes and ideas on total facade systems that you may not otherwise get in a more traditional setting. Allowing the design team to explore options and push the boundaries of design and manufacturing to develop a better system that meets the aesthetic qualities desired, but also the environmental ones. The facade engineering team assists in the design, as mentioned earlier, but can also assist in the procurement of the system using contacts in the industry for all components in the design. They can assist in evaluating fabricators for special materials. They can assist in establishing enhanced quality control procedures to ensure the desired design aesthetic and the desired performance of the facade are being maintained. And of course, that the design is once again protected, similarly to the design of structural glass systems. Something that we are seeing more and more these days with the higher demand for custom systems and better performing systems. Taking the knowledge and experience from all the projects we consult on and all the systems we see with the different glazers, allowing the consultant to contribute to the project in ways a simple design assist process on its own would fail. So let's take a quick look at 3 projects we're currently working on here in the local market. The first one is 30 Bay Street, or otherwise known as The Hub. It's a first-class office tower designed by Rochester, Harbour and Partners out of London. We designed the mullion system based on several different glazing size options for parametric costing studies, derived a transfer system within the transom itself to allow for anchors to be placed outside the mullion locations, which was required to the diagonal hanger system used in the structure itself. The glazing system was optimized, and the triple glaze system was fully loaded with dual coatings and warm edge technology. We also verified the thermal performance of the system, which was challenged by the fact that it was 100% vision glass, so no insulated spandrel panels. Flat glass was a strict criteria for the design team. So in order to allow the use of heat-strengthened glass, we devised a strict quality control program, which included the use of polarized light on the tempering line to help control the visual distortions caused by the tempering process. We looked at the high-span cable wall at the lobby, concentrating on a system that could work around exits and wall jam conditions. Also needed to design the backup structure for the Sky Garden, taking a holistic approach to combining the steel and aluminum elements together to minimize structure where possible. The project also required a review of the historic building at the base of the building that is part of the development, existing conditions, as well as tie-in details for the new atrium space attaching to the building. The second one is 1 Bloor Street West, or called The One, a super tall residential building at Yonge and Bloor designed by Foster and Partners out of London. A custom facade system that is complicated by a unique structural system. We had a lot of close collaboration with the architect in establishing the design of the system itself. The facade is unique and has challenges with cantilevered glass panels over the spandrel, as well as the detailing of the diagrid and horogrid elements. The therm models were used at all critical interfaces to ensure we addressed all condensation issues. The design continued to custom lobby, glazing options and details, and culminated with intense quality control initiatives by RJC during fabrication, erection, and testing of the mock-ups in both Asia and North America. A lot of hard work and a great team effort for everyone involved. Lastly, King Street West project, another tall residential project with 2 towers designed by Gary Partners out of LA. Challenges abound with the non-traditional floor plates, materials, and shaping of the elements. This project has several challenges and is benefiting from a design assist process. We are working hand in hand with the glazing company in developing the connection details, mullion sizes, and optimizations of the metal panels, reviewing and approving alternate standards that help reduce loads and thus material thicknesses and costs in the facade itself. And similar to 30 Bay, looking at sizing all the secondary steel in coordination with the cladding system for the crown elements and the canopy elements, reviewing these design elements holistically so that we minimize the amount of structural steel elements and improve on the aesthetics of the overall system, because we do not ignore the contribution the glazing system has on the overall assembly. So you've heard me reference the phrase protecting the design throughout this presentation. In my mind, this is a key to any successful project, especially when the systems or elements are custom and require us to push the envelope. It entails a complete facade design, an engineered design, and an equal partnership at the table during the design assist process when one occurs. Again, reinforcing the idea that we can bring all the experience from different projects, designs, and contractors to the table. With all the issues around our environment, as a facade engineer, you quickly realize that being a structural or facade engineer is not enough. Designing the facade on its own is not enough. Why is that? Enter climate change. We only have one planet. February 2022 was, on average, 1.19 degrees warmer relative to the years 1880 to 1920, the 5th warmest February on record since 1880. Our concentration of CO2 emissions have increased by 50% since 1750. And that doesn't sound too bad considering that was over 2.5 centuries ago. But it has increased by 15% between 2000 and 2022 alone. That is 30% of the increase in emissions since 1750 in the last 2 decades. Oops. So I hit something. It's not showing up on the screen, is it?
Is this the one you're on?
Just a second. This one here.
Okay.
All right, sorry about that. Climate change is not new. It was discussed in the early 19th century, but gained currency in the late 80s. The Kyoto Protocol adopted in 1997, the Paris Agreement in 2015, Greta Thunberg in 2018, and then obviously the Climate Change Conference in 2021. So what does this mean for us? As a consultant, as a developer, as a constructor, what is our responsibility? We need to help protect parties understand the importance of the facade in achieving these goals. A quality facade limits building energy loss and therefore helps reduce the operational carbon intensity of the building. By choosing quality materials, the embodied emissions of the facade can be reduced as well, but there is a balance. A higher carbon intensity in a facade can be offset many times over by energy and carbon saved over a lifetime of service. The clearest example being the extra embodied energy in fabricating a triple glazed unit over a double glazed unit. The triple glazed unit may have 50% greater carbon footprint than the double glazed option, but could save you hundreds of times of tons of carbon over the life of the building of the facade. So let's take the holistic design approach. Let's go beyond just building envelope reuse, but look at the whole system and the effect it has on the whole development. Facade engineering, energy modeling, air tightness testing, carbon counting, and life cycle assessment should play a role in the design of the facade. As an example, this project in British Columbia, which is currently in design development, the facade design was part of an iterative design development process, looking at optimizing passive performance. The horizontal and vertical shading element options were based on the building form and site orientations. Through detailed analysis, solar gains were mitigated, and the building is able to limit overheating hours without the addition of mechanical cooling. The facade itself is designed as a panelized wood assembly for thermal performance and low embodied emissions. A high level of assembly airtightness is also incorporated into design to assist the whole building in achieving the necessary thermal energy demand intensities and total energy use intensity requirements. How do we apply this? By taking an enclosure-first approach. Designs can be both elegant and intelligent. We do not have to sacrifice form for function. We have an extensive tool belt at our disposal to ensure we design a smart system and the tools to ensure we build a smart system. But naturally, we still need to balance all the essential criteria of a good envelope, elements that create the right environment for the occupants, like natural light, noise mitigation, and overall comfort. There are many obvious design considerations that should always be considered. IGU performance, structurally, mechanically, visually, and acoustically, passive shading to reduce cooling needs, photovoltaics, whether as a rooftop grid or integrated into the facade elements itself, choosing low conductivity materials, like we don't want to give away energy for free, minimize or eliminate thermal bridging. We spend time, effort, and our clients' money to design a good facade, so don't short circuit those efforts with thermal bridging as poorly designed attachments, and pay attention to the transitions. Don't let energy leak out around the perimeter of the facade itself. I'm going backwards, that's why I'm hitting the wrong button. Sorry about that. Materials matter. The structure and the enclosure facade of a modern building can account for up to 90% of its embodied emissions. The enclosure facade is the most important building system affecting the operational carbon footprint of the building. An LCA is the methodology for assessing environmental impacts associated with all the stages of the life cycle of a commercial product, process, or service. Environmental impacts are assessed from raw material extraction and processing, which is cradle, through the product's manufacture, distribution, and use to the recycling of the final disposal of the materials composing it, which is to its grave. These images are from an RJC LCA project which compared various structural concepts and material options to identify the least impactful design approach. The image on the left is a schematic section showing options for concrete, steel, and mass timber systems. The image on the right is a dashboard screenshot from One Click LCA, one of the tools that we use, showing the relative impact of materials, transport, and end of life. Materials, extraction, processing, manufacture is roughly 80% of the embodied emissions. And how much less would this percent be if the structural solution could all be in wood or local wood? The takeaway for this presentation is ask yourself the question, what is the embodied footprint of the material I'm considering, and how do I count the kilograms of CO2? Consider all the factors. This chart of bar graphs shows the relative performance of various primary structural design schemes of mass timber, hybrid, manufactured woods, hybrid alternatives, and concrete. And not all materials are obviously created equal, but all materials are as good or as bad as they might first appear. It depends on the lens you're viewing your opportunity. We obviously take a look at 2D and 3D thermal models for typical and complicated details, once again ensuring that we are looking at what critical elements may need tweaking in order to meet the performance specifications of the assembly itself. And not all elements need to be thermally broken. This is a low conductivity clip and not a true thermally broken clip, but it works well. It's relatively cheap to fabricate, but performs well because of the material properties of stainless steel. Thermal comfort analysis is critical to guard against uncontrolled overheating hours. This becomes more critical when we consider future climate loads. It provides a great deal of information for the design team, especially on mechanical system needs, as well as for the client and the end user. Building commissioning is critical to project success. Consider your testing friends as project collaborators. Help the installers troubleshoot and optimize performance during the course of fabrication and installation, and ultimately prove that the system is behaving and designed as intended. But it's not just new builds. The retrofit market needs alternative approaches. Current approaches are leading to slow incremental action. To really be effective, we need to consider deep energy retrofits. Consider overclads and effective double facades where practical, less disturbance to occupants and buildings can remain in service, or a complete renewal of the facade and systems with an opportunity to alter or improve the building aesthetic. But we need to move faster. Even moving at 8 times faster than the current rate, we will fall short of meeting our targets by 2030. So deep retrofits. Avoid embodied carbon emissions. We're improving the marketability of the building, extending the life of the building, and have the biggest impact on meeting reduced greenhouse gas emission targets. We model the systems considered, apply future climate loads, and we can look at dynamic facades, durable facades, facade overclads to reduce your operational carbon footprint. And here are 3 projects that we're just doing some work on right now that include overcladding or recladding. The Toronto Eaton Centre Skylight project, which is happening right now, where we are removing some of the structural bracing elements to create more vision glass, and we are also taking away a lot of the aluminum sections and creating much larger pieces of glass for better transparency. Allen Gardens, where we are recladding the greenhouse itself, the dome itself, the main dome, and using the solar study to find out where we should apply most frit to try and keep the solar heat gain down as much as possible. And HSBC building in Edmonton, where we did a complete retrofit, where we gutted the building from inside and outside, replaced all the mechanical, electrical systems and the facade system with triple glazed, and opened it up to a new Class A category that it didn't have before. So a couple of quotes. The science is clear. Canadians have been clear. We must not only continue taking real climate action, we must also move faster and go further. As Canadians are increasingly experiencing across the country, climate change is an existential threat. Building a cleaner, greener future will require a sustained and collaborative effort from all of us. That's from our lovely Prime Minister. We will not achieve the required greenhouse gas performance from our existing building stock by working within current market structures and policy approaches. Policymakers and must understand the potential from treating buildings as public infrastructure. This perspective invites us to value the national level systematic and social benefits of retrofitting buildings on a scale and a pace that is responsive to the climate emergency. So what are we waiting for? Let's get busy.
Excellent. Thanks, John. One thought to take away is that idea that design expertise and having a holistic design team is such a key element in terms of creating these buildings that we need to have to meet our climate emergency. So yeah, kudos on that. So next up is Piero De Lucia, who's the regional director at Rayner's Aluminum. Thank you.
Thank you. Good morning, everyone. Can you hear me? Yes. Good morning. My name is Piero De Lucia. I'm a regional director for Rayner's Aluminum, and we are pretty glad to be here in the presenting part of this really interesting event. Today, I would like to highlight something that's quite unusual, I would say, in such seminaries. It is about the role of virtual reality in the design of a building. But before that, please allow me to introduce you, 2 minutes, the company we represent. So, Rayner's Aluminum is a European leader and specialist in developing solutions for the development of the building. There are many ways to identify us. We have a worldwide network, innovation, collaboration, R&D. Basically, we are a family business, still family-owned, created in '65 by the father of these 5 persons you see here in the picture, Jan Reiners, who was a fabricator in the region of Antwerp, Belgium, Flanders, and he was developing his own system, fabricating it and installing it. And after some years, the fabricators of the area decided to started asking for that system. Can you please sell it to us? And he came with the idea of focusing on development of the systems and on all the value proposition that can be brought into the market through the fabricators. That's when Rayner's Aluminum started. Unfortunately, 8 years later, he died of a car accident. So it was that lady with the dress in orange. Unfortunately, the colors are a little bit. The lady sitting with the clothes in orange. They took over the company. She was 28 years old. It was a company of the equivalent of $4 million. $4 million back then, and we are now at a company that does 700 million euros worldwide, more than 40 countries established, etc. So when you develop a company, especially worldwide, you need to align on values, so on a mission. And for us, it's pretty straightforward. When we sit around the table with stakeholders, with architects, engineers, developers, we need to understand that we are there to bring our expertise. So we need to improve that project. So our goal and mission is to improve, increase the value of buildings, and enhance the value of living and working worldwide within this building, and within this building that are enveloped by our solutions. That are sustainable, as has been explained before. Of course, in Europe, We are quite straightforward regarding quite strict regarding this aspect, and innovative. Our motto is Together for Better. We really try to do it understanding the trend and the needs of the local markets. That's why we build up local branches like the one we have here in Canada. So as I said, we have an international footprint, our headquarters in Belgium, more offices in more than 40 countries, more than 5,000 partners who are the fabricators to whom we provide them with our solution. On one side, the product, the technology, but also Industry 4.0, automation, digitalization. We try to really leverage them up against the competition. More than 17 logistics centers, et cetera, and we also developed ourselves in terms of testing. I will explain this later. And of course, since 2019, the family decided to invest in Canada. And as a matter of fact, in the last couple of years, the branch in Canada has been the fastest growing among the other branches in the group. It means that there is some ferment going on here, some dynamism that we can really focus on. Some facts and figures. Last year, 650 million euros development, more than 2,000 employees. So the doubling almost the turnover in 6 years, 7 years. This doesn't come, let's say, as magic. The family invested massively in the last 3-4 years in developing the company at any level. And that's the strength that you have when you have still a family-owned business with such a volume. So our product range is quite extensive. We can really cover all sort of projects from windows and doors, sliding foldings, and here I would say we're really topping the performances that one can require from such solutions. Curtain walls, of course, standard and custom-made, roof and conservatories, and complementary systems like shadings, etc. We try to be innovative and forward-thinking. The world is changing. We need to be agile. We need to invest constantly to avoid being obsolete. We see this in Canada. Regulations are changing. Also the trend forcing companies to put in questions again their methods, their operations. That's why we invested in more than 100 engineers, separated in 2 departments, the R&D and the bespoke solution department, to make sure that we manage to answer to the challenging trends, both in terms of aesthetics and in terms of performances, air, wind, water, etc. And of course, these engineers, these studies are supported by our test centers. The family wanted to have a huge investment years ago into developing 3 test centers worldwide, and the biggest worldwide in the private sector of aluminium is the one we have in Belgium, where we really try to cover all the aspects of performances that an envelope should grant to a building. Comfort, air, wind, and water, acoustics. It's getting more and more a topic, we feel. Sustainability. Of course, you can describe a beautiful element, a beautiful slider that makes 4 meters high. Sorry if I talk metrics. But of course, what happens after 10,000 cycles, 100,000 cycles? This is what we do. We test the cyclicity, we do cyclical test, durability test, we measure the tolerances, safety, bulge resistant, impact testing, fireproof, bomb blasting. We really cover all sorts of requirements. And of course, we invest massively in working. I said the motto is Together for Better. Working with the architects, with the stakeholders, allow us to avoid being obsolete and too far from the reality of the context of the one market. And also we managed to really develop the relationship through the supports that also goes via the 3D and virtual reality environment. That's the topic of today. Virtual reality, a game changer in the decision-making process of architectural design. So some years ago, the family, as explained, they try to really understand every time how can we promote innovation and be a reference worldwide in excellence when it comes to envelope design. So we started getting interested and investigating a bit further into virtual reality. What is it in the end? The principle doesn't change because we still have two eyes. So it is about positioning two images with a slightly different perspective, and the brain will consolidate this image in a depth, an image with depth. That's virtual reality in the end. So we started analyzing and investigating on what was on the market, but we realized that these tools were not really useful because the decision-making process involves different stakeholders with different vocabularies and backgrounds. You have architects, you have engineers, you have developers. Everyone speaks his own language. So the user-friendliness of such a technology is in need of a collaborative experience. That is why we started getting interested into the cave, which is a concept that's used in automotive. Mercedes, BMW, they all use this technology because it allows them to develop very fast prototypes in an immersive and collaborative environment. And of course, we are the only ones that are applying this concept for architecture. So I will let a small video introduce the technology.
Welcome to Avalon, a space to explore architecture through a shared virtual reality experience. Did you ever wish you could walk into a building that is still in the design phase? Avalon can take you anywhere you want. 25 projectors make architectural designs come to life in unequaled resolution, with cutting-edge laser technology creating the most vivid colors, contrast, and brightness. Active 3D glasses create a natural spatial awareness, and as a user, you are instantly immersed in a true 3D environment that creates an incredible sense of scale and depth. You are able to share the experience with your partners, allowing you to discuss and evaluate your projects before they are built. Avalon is a collaborative working tool, offering a joint experience between architect, contractors, investors, engineers, fabricators, and Rayner's experts. Virtual reality is set to play an important role at all stages of the architectural process, from evaluating design options and showcasing proposals to detecting construction issues before breaking ground on site. Starting at the conceptual phase, VR has proven to be effective in exploring the relationships between spaces. VR gives you an immediate feeling of being inside the building. You can experience the impact of light on a room, or evaluate the different interior viewpoints. The spatial realism makes Avalon an incredibly powerful tool to communicate design intent. When the architectural design is further specified, BIM files are effortlessly translated into VR, providing architects with even better tools to communicate about their choices and improve their designs. Enabling architects to effortlessly move between BIM and VR truly revolutionizes the way buildings are designed. Avalon allows you to explore your projects inside your usual design software. Its powerful main workstation handles 3D models produced in any commonly used software in the architecture industry. By tracking the visitor's movements, real-time rendering engines create the ultimate VR experience, from initial sketches through detailed technical models and realistic scenes. Before your visit, you provide the 3D model of the project. In consultation with the building team, the objectives are set and the model is adapted accordingly and prepared for VR. Different options can be prepared to compare several Rayner's systems, configurations, bespoke solutions, or specific design variants for your project. Avalon is perfectly suited to create diverse virtual mock-ups. You can make sections, explain complex technical setups, or examine specific construction details or project solutions. This new way of virtual prototyping reduces costs and increases efficiency drastically. The high-resolution real-time renders allow you to see every detail so you can experiment with different configurations, evaluate simulation or BIM data, and further improve your design. You are able to experience Rayner's systems up close and compare the different solutions for your project. Discover Avalon, the space where future projects become a reality.
So why it is interesting to investigate this way of designing a building? Why virtual reality can be interesting? First of all, avoiding mistakes. There are studies that say that, I don't know if it's a Photoshop, but it looks like that because, I mean, if I was the architect, I wouldn't be that calm. Anyway, there are studies that say that in processes, in human being processes, 80% of the mistakes, the errors that appear are not that complex. They could have been anticipated. Especially if you could put together the contrast between the different trades, the different intervenants of the process, right? Secondly, taking decisions. And we know this, as I explained this before, an architect, a real estate developer, an engineer, a fabricator, an end user. Everyone has a different background, a different vocabulary. How can we bring these people together? I was bringing the same anecdote. Years ago, I was developing a hospital in Belgium, a project, and I remember I was coming with the drawings, and one of the guys that had to approve them was a doctor. And he was keeping, I don't understand anything, I don't sign. Of course, there was a contract, there are penalties and all these things. So how can we facilitate the process and the trust also at the preliminary stage, when things are a little bit relaxed, not when we discover things a month before the start of the works. So we are developing projects in this unique, immersive virtual reality tool, a bit worldwide. From Bangkok to Vancouver, all the stakeholders are visiting us. We do the project that can be purely on a concept evaluation, even from SketchUp sometimes, to have an appreciation on the perspective kind of view, and not only on an immersive, on an appreciation on how it's going to be in some years, the building. The technical evaluation, Navis work, for instance, so what I said before, the different trades that are interconnected, and we can evaluate indeed the contrast. And sometimes, this is especially with a real estate developer, high-end quality design evaluation. We use this sometimes also in sales. The developer bringing investors there to make them understand how the project is going to change. It was the case for Battersea in London. For those that like Pink Floyd, that's the image on the album Animals. Of course, it's an industrial, everyone has an idea about an industrial area reconverted into high-end apartments. How can I transfer this idea to investors and bring them with me? Some examples, as I said before, design concept, a tower, to evoke the emotion, the feel about the project itself, the design itself. Some example again, Al-Wakra Stadium, Zadid Architect, we work with them. They were at our premises, and they simply had the project on the USB. We loaded it, and it was like seeing children, and the architect became children. And they started to say, okay, I need to check something. Because this building, for those that like soccer, this is a building that is going to ensure the air-conditioned air pulse before the match. So the roof is going to close. They're going to pulse air condition because outside is 50 degrees. And then when the match starts, they will open it. Of course, sand and environment, they need to maintain this technology. There are bridges over there for maintenance. And the architect and the developer could say, okay, can we walk on it? Can we feel like, is this safe? Do I have a safe feeling when I have to do that job, right? That was a really simple thing. But yeah, it increased the trust with the stakeholder. Sometimes we do mock-ups. It doesn't mean that we don't have to do the mock-up at the end of the process, but maybe we can already discuss topics and facilitate and filter out a little bit the process in the beginning, making multiple mock-ups. It doesn't cost anything. And at the end, we will do a mock-up that makes more sense for everyone. We will anticipate a lot of questions. Towers, of course, pre-glazed. This is a tower in Serbia. 3-4 years before the first element being installed, we have the architect, the engineer. The architect designed something. The corner element has been designed like glass to glass, glued. Of course, this is not going to be possible. We had the wind tunnel test, the wind load, and we had to introduce for the inertial needs this inclinated profile that you see there on the end. Yeah, we could anticipate this 4 years before the discussion of the shop drawings, right? And we brought the architects and the promoter with us on this one. They could also check the building from the perspective of the viewer. When I propose a drawing that's maximizing the element, I feel like you are destroying my architecture, right? So we managed to bring everyone together with us. Another typical example, this is in Amsterdam. I was personally involved. So multi-residential high-rise. You start going up with the floors, and you have the wind load creating stress on the mullion. We need to introduce a reinforcement. Everyone starts to stress. Who's going to say this to the architect? Who's going to say this to the investor? The investor doesn't want it inside. It's going to ruin the fruition of the space. And the architect doesn't want it inside because you destroy the facade. So we brought them in Avalon, and we positioned ourselves at a fair distance to appreciate the aesthetics of the building. And I remember the architect said, "Can you please now position the reinforcement outside?" And we said, "It's already outside." So again, putting things in perspective, it's really the case. This is another project that we are finishing now. It's called The Quad. It's in Malta. I was also personally involved. Promoters, engineers, they all came. We developed a custom-made solution. And we managed to create not only the project itself, but we could show, that allowed us to show 3 years before the first stone, or the first square foot of glass, maybe it's more. We managed to show to these developers exactly what we planned to do, what the study that we did, the concept that we managed to develop. For instance, this was an example showing the anchoring system that we developed. Given that there is this curved part of the building, how do we handle the tolerances? Even the investor understands the concept. You build up trust at a very early stage. This helps the full process to go on the right way. This is a project in Brussels, another complicated pre-glazed solution. Why? Because there is these elements of marble that need to be attached to the pre-glazed element that needs to be attached to the building. So how can we show the technological development that we did with our partner and make sure that everyone is on board with that solution, with that decision? How can we ensure that people are with us? This is an extension of a school in Holland, with an existing one. A project in Dublin Airport Hotel, bomb blast, also custom made, same thing, developer, architect, engineer, all there, taking decision, showing alternatives. This is also very important. It's not static. It's a virtual reality environment, so we can decide what we want to do. For instance, multi-residential high-rise. The architect comes with the first solution here. Of course, there is a price tag also, because we need to be competitive at a certain point. We need to make it enter within a budget. There is a huge glazed part. It will require some movement, some budgets to get the glass there. So simple as that, we created different models with the architect, with the developer. 2, 3, 4, 5 model, 8 models. And this model could be, were walked in by all the stakeholders, and there was a price tag per level, and they took their decision. So when you give alternatives also on the early stage, you create an environment that feels supported. Again, what I said before, we try to bring what has not been asked. That's our success. That's our expertise. Voila. Other complex buildings. This is, for instance, another pre-glazed system that is a little bit, let's say, complex in design. Again, there is a stakeholder and an engineer. How do you make this happen? How do you fabricate it? How do you install it, etc. And same thing goes for standard windows and doors, sliders, sliding systems. This is a complex. It's definitely not in Canada, as you can see. More in the Mediterranean, south of Spain. Same thing. We give the feel we allow the stakeholder to have the feel of the project itself, the fruition of the project itself, and then we can talk alternatives of the system regarding the system. The sliders here, that, for instance, have been offered, and they can evaluate. There's a price, of course. There is also a transfer of technical specs into a user-friendly way. Everyone can understand. And the developer can say, I want this system, for instance, instead of the other, because it is a signature for my development. This is a project also in Belgium. We have a lot of old industrial building from the Industrial Revolution age. We are trying to reconvert this into a co-working space. And here the topic was really about, okay, from one side, we need a system that reminds about that age, that aesthetics. It's the Cell 38 system. It reminds the steel system, iron. But on the other side, when you do all this complexity, what's the impact on the light when I'm working there and my clients are working in these spaces? What happens during the day, during the seasons? We can really simulate this aspect. Also, it's really possible to do anything. And of course, internally, we use it to do the proto studies of our new systems. And this is the master party, for instance. When it was studied 3-4 years ago, we have it now, of course, for the Canadian market. And of course, as I explained before, we are system developer. We partner with fabricators, and we try to empower them. One of the topics is also Industry 4.0. So we support our partners into the development of their workshop in the most efficient way possible. So we allow the client to visit the space and to change, of course, the machines and study the flux of let's say, of the work. It's easier when it's on virtual reality environment than when you have to do it when the machine is there. Voila. So this is a little bit to show something I feel interesting. Of course, we have a lot to say about our system, our approach for the envelope of the building. Our team is over there. Please don't hesitate to come and ask questions. We are glad to answer those. Thank you.
Thank you, Piero. That's really great. One piece that really strikes me is that idea about stakeholder buy-in. And when you apply that to a public building, you suddenly get into that idea of social resilience and equity within that community, because you get that buy-in. It's so important. Yeah, so fantastic. Well done. And next up, we have Shirley Bloomberg, founding partner at KPMG Architects.
No. Where's the clicker? So this is next.
Back, and this is the pointer. So if you want to,
That's next, and that's
back.
Thank you very much. Hello, everyone. I know we're running late, but take heart. I'm the last speaker before lunch. I'll try and be quick. So I'm going to talk today about 3 projects across Canada. The first one is located in Fort Severn, and that's at the northern edge of Ontario as you hit Hudson's Bay. The second one is at the University of British Columbia, and that is on the west coast, and the other one is on the east in Halifax on the water's edge. These are 3 very, very different projects with different scales, different programs, budgets, different climates, geographies, but the same technical and artistic challenges. And on all 3, we worked with a building science consultant and an energy engineer so that we can integrate building physics with our artistic design ambitions. So, I think it was John Krause who mentioned the National Research Council of Canada, and the NRC, as I understand it, has played a major role in establishing the quality of building science in Canada, which is why we were early adapters of the rain screen principles, as amongst other things. This project was for the NRC. They had approached David Fortin, who at the time was the director of the School of Architecture at the MacEwan School in Laurentian University in Sudbury. They wanted him to design 5 different prototypical houses for northern houses in 5 regions in Canada. David is a Métis architect, and what he decided to do, he invited 5 different Indigenous architects across the country to design in their region. For about 3 years prior to that, I had been working with Brian Porter, a colleague who has a practice called Two Row Architect, and Brian is a Six Nations architect, and we had been doing research with building science consultants and energy engineers into northern housing. So this, Brian invited us to work with him, and this was a great opportunity to actually test out our research and our theories. So this is what we ended up designing. The program that was required by the community of Fort Severn was a duplex, and it was for a combination of 1 elder apartment and a unit for a small family. The reason the roofs are so high is because the houses, not only do small families grow, but the houses also act as kind of social centers. So very often, if you're having a party or gathering or dinner, people will sleep over. So we created a loft in that extra height for expansion and just kind of an idea about just generosity and giving people choice. So we used local material cladding. All the families use wood-burning stoves, so we used galvanized roofs, metal roofs, and we tried to design them in clusters and as passive as possible. So we were clear that we had to design a process first before we put pen to paper. And Lawrence Holland, who's the architect on my team at the office, and Brian Porter flew up to Fort Severn. It's quite an arduous journey, and stayed there for 3 days because part of this, and we were clear as well, is that nothing could happen without a really robust community consultation. Because a lot of these communities have not been asked what their needs are, what their culture is, how they, basically housing to fit their needs. Also, this was going to be a self-build project, and Fort Severn has teams, construction teams, who are used to building wood frame kits, suburban housing kits from Winnipeg. So we designed the house to suit wood frame, to suit those skills. This is the historical context. The Askagan, which is traditional teepee, and then what you see is on the right is what people live in Fort Severn right now. The challenges are absolutely massive, and I'm sure a lot of you know much about this. Extreme climate conditions, remote locations. Fort Severn has a barge that comes once or twice a year, bringing materials. Everything else is flown in, other than the ice roads, which are, in the winter, which are decreasing in length. The time they're there is decreasing because of climate change. Fast-growing population. There is massive, massive housing crises. These kit houses, southern suburban houses, don't do well. Within 5 years, even new houses are riddled with mold and people are very sick. A huge number of houses have overcrowded conditions and rapidly deteriorating. And of course, without housing, you cannot solve any of the other issues. The landscape context up there, it's tundra. It's all muskeg, which is peat or bog. And they have a lot of tamarack trees as well. In the middle, that's Brian's shoes. It just shows you sinking into the muskeg. But there also is quite a beauty about it. And in the fall, you know, the colors, the leaves turn and so on. So, and you can see a view of the river. And people really, really value this landscape, and they still go out hunting and fishing for extended periods of time. So, the community engagement. Brian and Lawrence stayed at the Niska Inn and set up in the little community hall. And you can see some of the conditions. They toured a lot of houses, and they interviewed as many people as they could, from elders to young people. Because it is on permafrost, they had figured some stuff out. Chief Paul had installed a solar system, which is really good. They actually had running water. But the way they dealt with the muskeg is, it's gravel everywhere. They just pour a pile of gravel. So when you're in the town, there's no landscape. And also, there are these space frame foundations that they use, which we thought were really, really good, because they can adjust them every year because of the settlement. So our design strategies, and this came out of our community consultation, connect to the land. They really, really wanted that. Resilient community in every way, socially, economically, environmentally, and work in alignment with the natural forces, like they used to do in the olden days. We had to figure out how to build for extreme climate and remote logistics. And this is very, very important in terms of indigenous values, designed for 7 generations. These were the archetypes. You've seen the Askagan on the left. That in the middle is this really beautiful teepee. They all build their own teepees for smoking. And this was really quite beautiful. And then the other thing that really caught our eye was, this is the oldest house in Fort Severn. It's in disuse, but the wood shingles have this beautiful silver color. So right now, for some reason, they build in a suburban kind of pattern with houses along a road. So this made no sense to us at all. And so what we did is we designed these clusters. We chose a site, and in the middle of the site, there was, I think that works. Anyway, there was existing landscape. And there's nowhere for kids to play right now, so they don't really spend that much time outdoors. And in the summer, there's the mosquitoes, right? So what we also did is we built a system of wooden boardwalks fully accessible for everybody, so we could raise the houses up. People could actually gather there, add screen porches and so on. There's a lot of stuff to do with cars, snowmobiles, fixing pickup trucks, etc. So they need these kind of work yards where they park. That was outboard. And then in the center, we kept the landscape, and also the wind comes through there in the summer. That helps with mosquitoes, and that's where people can gather and play. You can see the square in the unit is for the family, with the loft at the second floor, and then the little rectangle to the left is for the elder. All the issues to do with hunting and fishing, big chest freezers, all that stuff we designed for. This was interesting. So what we did is we oriented these units to use the winter wind, which came from the west, to scour the faces where the front doors were, to get rid of the snow buildup. Otherwise, you can't get in your house. Stuff like that you don't get unless you go there and speak to people. And then, as I mentioned before, the summer wind that comes through. We also designed it so that these were as passive as possible. And the places, we oriented the living rooms of the homes towards the sun, to the south, and the bedrooms to the north. So this was a lot of discussion about this, and it's a kind of ongoing investigation. So we designed the exterior wall to take any lightweight cladding, and in this case we were proposing that they could use larch, make shingles from the larch, but it could take any cladding. The main exterior insulation is exterior, 8-inch board, R32, and this is very important, that the airtight barrier for AVB was to the inside of that, because we had to prevent the dew point from happening inside interior of the house, because humidity levels are very high, etc. The other thing we did was the framing, 2x6 framing. We had a 24-inch on center. Why? Because it's less material to bring on the barge, and it's cheaper. There's a controversy between the NRC engineers and our energy engineer, who thinks you don't need bad insulation on the inside. And then you've got the interior finish, which would be drywall or plywood. And this allows for people to, bring conduits in there, to hang pictures and so on, without damaging the AVB. And that's the night view. Good news is, Chief Paul has secured funding for one duplex. The bad news is we're having a hard time getting a hold of him, but hopefully we can use this as a test demonstration. The second one is completely different. So if those of you who know UBC, it started out life as a large commuter campus, quite suburban, and they, in the mid, around 2010, so whatever, or 12, they started a really good program of building mixed-use hubs, residential, along with academic program and social. And this was the first one. What they also did was, for some inexplicable reason, this is phase one, were 2 buildings, and it included the art school, which is the part with all the color, and the residence you see behind with the concrete cladding, and then phase 2 is to the right. The budget for this was $210, including all the, academic and all the rest of it. We brought it in for $215, and then for some other bizarre reason, it opened in 2013. In 2016, we finished phase 2, which was half the education department, plus residential, etc. And that was $185 a square foot. So we were a little concerned. how to meet the budget. So we decided to forget the way we usually do things. We had an excellent CM, and we sat down with them and their trades, and we went through each of the building systems that we wanted to work with to figure out how could we do it most economically so that we could afford something. So what we did was used a lot of graphics and color. This is the inside of the art school. And then one thing we did was we actually developed an insulated precast system, exterior precast system. So it's quite a modernist white brick campus. So the idea was we would do precast panels and create ridges so it looks like brick. So we valued engineered this, and in phase 2, so we knew exactly how wide, et cetera, et cetera. In phase 2, we actually were able to get better precasters, and they told us that if we designed the panels 3 stories high, that would be even cheaper to do. This is just to show you that we were able to balance it out and still afford some customization in the curtain wall system. And we even spoke to the Millbrook trades, and they said, well, maybe because we wanted to use Western red cedar. So they said, okay, the cheapest is rough sawn. So that's what we did. So looking at the building, you wouldn't actually think it was, that was $185 a square foot. These are the details. So there were a few things about this. Basically, 75 outer wide of precast, 75 of insulation, and 75 inner. We had a kind of shiplap condition for the outer because at the joints at each floor, we had to be very careful to make sure there was no air and water penetration. The connectors were very, very important. So we had to use either stainless steel or fiberglass were the choices for us, because you wanted something with a low transmission coefficient to prevent thermal bridging. And what were the other things? Oh, I know. What we saved a huge amount of money because the interior withe was perfectly beautiful precast white concrete. Didn't do a thing with it. That became the interior. So no drywall, none of that. And we used electric heating. The thermography on, that they did when this was LEED Gold, the thermography showed that it was working extremely well. Very, very simple. And this is the phase 2. Here you can see the longer panels. And our envelope consultant has told the project architect who was working with me that he still recommends this system because it works extremely well, and UBC has used the system on all their other hubs, and the moral of the story is we should have patented it. So, a very, very different project, and this is still in design. We've just completed design development. We won the competition to do a nude art gallery in Halifax for Nova Scotia. And this was a whole new way of collaborating. There was a lot of focus on the deep history of Nova Scotia and the Mi'kmaq people who've been there for over 13,000 years. So my partner Bruce and I worked with Omar Gandhi, who is a young architect in Halifax, used to work with us as a student and as a grad. And we partnered with Jordan Bennett, who's a Mi'kmaq artist, and Elder Lorraine Whitman, who is she's the head of the National Native Women's Association in Canada. And also Mark Ryan from Public, who is a wonderful landscape architect. And it was basically, it was almost like responding to Truth and Reconciliation. The project, in a way, was bigger than just a design. And we collaborated, and we were very open and did a lot of consultation with the Mi'kmaq people and other communities in Halifax. And it wasn't that easy. There were kind of bumps along the road, but in the end, I think we are all of us so thrilled that we did this, because we were able to create something we think that we never would have had we worked on our own. So this is the site, that huge empty lot. Halifax is pretty interesting. I'm sure you know it well. And what we did is we used the metaphor of an eel, which is very important in both Mi'kmaq culture and Scottish. What's the word for Scottish? Gaelic? Not Gaelic. Anyway, I'm sorry, but other cultures. and it lives, the eel lives both on water and land, and what we needed to do was to organize the site. We needed a kind of sinuous form so that it would work. So this shows you a plan. This is the main street on the left there. And so we have on the south side of the building an art yard, and at the water's edge we have a public space. This is the plan of the building, and at the ground floor it's a very, very public space. It's got cafe, you know, retail, bookstore, education studios right on the ocean, and so on. So what I'm going to talk about is the curtain wall that goes from the sort of west at the entrance on the north side to the east, facing the ocean. On the south side, we did a kingspan product because there was no way we could afford to take it all through. So this is a facade study we did. It's a complex kind of layered facade. So on the ground floor, what you see, first of all, is a dye grid, a steel dye grid that we clad in local timber for fireproofing. And also as a kind of reference to Halifax. On the ground floor, which is largely public, as I said, we have a double glazed system, but the IUG has a laminated outer pane. We did that so that we could actually avoid using glass fins. So this is structural glass, no mullions. And also there are curved parts. So that's a kind of look ma, no hands kind of thing. On the second and third floor where the louvers are, those are gallery levels. So we have triple glazing there. And on each floor we have, you know, that's the kind of promenade. On the top floor it's offices and multi-purpose space. We did lots of studies to look at, you know, do we do vertical fins? Do we angle them? Unitized and with outriggers. Anyway, as you can imagine, budget was quite challenging. And working with our construction manager, we basically came to the triple glazed curtain wall and then with these vertical louvers. Here you can see there, each condition was quite different. So at grade, we actually, the curtain wall has to allow for natural ventilation to enter. That then filters up. The floor level at level 2 does not go all the way to the glass, so it's open there. Level 3 does, and then is vented through the stair and through the roof. And there are other areas where we can actually have the air travel up through the building. It's quite interesting because with natural ventilation, ocean cooling, we're doing that. And the louvers, we don't need any mechanical cooling for the public spaces. It's all from the slabs. So that's pretty good. And it helps that it's mostly north-facing. So these are studies where it's pulled back from the facade, then we need a guard. And this is, you know, we're still refining all this, but just so you can kind of understand how the structure works, the diagrid in brown, and then the triple glaze system with the louvers. These are drawings. We've done gazillion drawings of that. And we will continue because this will be basically design assist. We also worked with Transolar, who are, we've worked with them for about 15, probably 18 years by now. They're pretty amazing. So one of the issues with all the promenade along the north was the curators didn't want any light or glare into the galleries. So we did the analysis of the facades, and you can see where the problem is on the north and east and part of the west, and not in the south because it's largely back of house and largely closed. Looking at point-in-time illuminance, looking with the doors open, closed, etc. Annual glare, all of this basically fed into our plans, which then produced, and we're still refining it, the pattern of how dense or how open the louvers are. So we have to check that in a very, very specific way. This is a view from the inside, just a sketch. What is really nice is this is the ground floor. This is a double height space between 2 and 3 where they'll probably have their openings. We've designed this as net zero ready. It's all electric, so when they clean up the grid in Nova Scotia, it will actually, they're able to have it perform as net zero. So we thought that was extremely important. That's it. Thank you.
Thank you so much, Shirley. That's fantastic. Really amazing work. I look forward to seeing the final pictures on the Fort Severn project. That's going to be really amazing if you can pull that off and get it across the country to all the Indigenous communities that need that. Yeah. So fantastic. It's lunchtime now. Thank you for attending into session 2. We're going to be moving to session 3 after lunch. We'll come back at about 1:40, 1:45. Thank you.
Hello. Can I request all of you to please be seated? We'll start in a minute. If you can just take your seats. Bro, can you switch? Switch. Right, we will start. John, can I have you? Right. Is the mic on?
I think, yep, mic's on. Awesome, thank you. All right, well, thank you. Welcome back. Session 3 for the afternoon. And first up, we have Carol Phillips. She's a partner at Moriyama and Tashima. Welcome.
Is it on? Yeah. Is it on? Okay, thank you very much. The timer hasn't started yet, but this is I'll admit I'm a bit nervous. Oh, it's started. So today I'm here to talk a little bit about 2 projects that I'm working on in the Toronto area. Both are mass timber and very highly sustainable. Very briefly, I'll just introduce a little bit about my firm, founded almost 65 years ago by Raymond Moriyama. He was soon joined by the late Ted Tashima. And the image on the screen exemplifies some of the core values of our firm, a kind of appreciation for land and a melding together of building and landscape. And the biggest gift that I would say that Raymond and Ted gave to us was to found a practice. This is the Ontario Science Centre, a project that endures, and we've had the opportunity to revisit and see those relationships between building and nature. But one of the biggest gifts that we were given as a practice, and there are some in the audience here from the firm, is that they founded a practice based on principles, not a house style. Regeneration, leaving sites a little better than we found them. Generosity, exploring the latent potential, the latent social and social justice potential in all of our projects, and generating unique solutions for our clients and their unique sites, whether that's in the desert, the Canadian Embassy in Tokyo, and as we are a youthful, diverse office, these principles live in all of us. The next 2 projects really exemplify some of these relationships and how they've been taken forward into the world of sustainability and mass timber construction. And I will be focusing on the facades, although there are many, many stories to be told. One of the things I want to mention about the next 2 projects is that they are authored by essentially the same consulting team. Moriyama and Tashima architects, Fastenap structural engineers, Trans-Solar sustainability engineers, and the Integral Group are all common, as well as Stephen Kraft from CHM Fire, are all common to both of these projects, but very, very different solutions. The first one is the OSSTF headquarters and multi-tenant commercial building. This is for the Ontario Secondary School Teachers Federation, and they have a site on Mobile Drive on the edge of the Don Valley Ravine. And I show these images for those of you who are not from Toronto, and even for those of you who are from Toronto, because this is our city, it's green. And their project was, like our firm, really founded on principles. They represent the educators across Ontario. They have to be responsible, fiscally responsible. So while there are lots of demonstration projects and really aspirational projects that are reaching for net zero carbon emissions, mass timber, for the Ontario Secondary School Teachers Federation, this had to make economic sense, and it had to prove to their constituents that this made financial sense for the long term. This image shows basically a concept of a building that restores the ravine, that connects people through health and wellness to their environment, and that occupies a smaller footprint and recognizes a larger context for the project. Now, some of the things that we did working with our larger consultant team was to really prioritize restoration of the ravine, engagement with the ravine by the use of outdoor spaces. In terms of the broader environment, we looked at how air and light would feed this project. So there is a full solar array on the roof, as well as a solar chimney, which not only brings light deep into the project, but is also part of the natural ventilation system. Some of the sustainable principles about this project is it has a taut envelope, so it's a very compact footprint for the occupancy. It brings daylight deep into the project, and the two metrics on the bottom are important with respect to facades, because the story I want to tell about this building is the role that energy modeling played in our decisions. So when we talk about highly sustainable buildings, this building is LEED Platinum building. If not for the clay in the environment and the stormwater management issues that we have here, this would be Tier 3 for the Toronto Green Standards, but we just can't get enough water into the ground. We ended up with a 50% window-to-wall ratio, and that's not what you usually see when we're talking about passive house and highly sustainable buildings. We're usually talking about 40 or less. I show these metrics about the energy performance of the building because, interestingly, it sort of speaks to the culture of the building. We're talking about the reduction here, because at every step of the way, the energy model and the financial models had to make sense. So investment in construction had to have long-term life cycle payoff for the OSSTF. So all of the metrics are shown in reductions because it shows how over time this project will perform and pay back to the membership of the OSSTF. Some of the social things that we wanted to do as we changed culture for a 100-year organization was to give democratic access to daylight, meaning that all of the workstations, and those of you who do office layouts understand that these are good principles, to put the offices inboard, the dark program inboard, and to actually give the light and the view back to the community. These are what the spaces look like. Access to outdoor spaces on every level. This is on the 3rd floor. The building is 3 stories tall with a limited basement. It is hybrid construction. This is a really washed out slide, I'm sorry. It's concrete, timber, and steel construction, so it's a true hybrid. And for those of you who are working in the world of mass timber, we have to talk about hybrid. Steel, as long as we're doing basements, we can't be talking about timber basements, so we can all play nicely in the sandbox together, and so for those of you who represent concrete and steel, I think we just need to get together and get on board and reduce all of our carbon. But this is the context of the project. So of utmost importance was daylight and view for the OSSTF. And what was really interesting was when we ran the models, when we were using passive ventilation, when we were using geothermal in this project, and when we are using a high-performance envelope, what drives the energy model really are plug loads and lighting loads. And really where the energy model took us was that we wanted to have a 50% window-to-wall ratio to actually reduce the lighting loads in the project. For a west-facing facade as this was, we needed sun shading. So the entire architectural expression of the building started to surround these sun shading devices, which we wanted to angle so that we could maximize view, and also clad the underside of the sunshade in wood to give the project a wood identity even as you approach from the north face. So we ended up actually wrapping these sunshades around the building, optimizing them to have daylight. So the ones on the north face are more shallow than those on the south face, the ones on the east more shallow than those on the west. And everything was sort of designed and optimized based on the energy model and the light penetration into the building. So skipping forward to the building's under construction now, but what I want to show here is that we, with the blessing of the OSSTF, shared our project with Kelly Doran, who is a professor at the University of Toronto running what's called Half Studio, where his graduate students pushed a number of projects from throughout North America and Europe, and these were only a third of them, through a series of energy models and embodied carbon analyses. And what we found, and they modeled our project, and this is a little bit inverse because what's shown in green is actually the worst performers, and what's shown in red is actually the best performers. Despite the fact that our entire facade has a CLT backup, and that's the red one that you see there, we have an aluminum facade. These members on the bottom here, these HSSs that actually supported that sunshade, really pushed our embodied carbon over the top. So despite all of the well-meaning of this project, the excellent sustainability agenda, the great performance, the CLT use, this analysis, which we kind of wish was done while we were designing, showed us that our embodied carbon in the building was actually, tipped over by these sunshades. So the big lessons that we learn here are how to approach a building holistically, how to look at the energy performance, to actually look at the thermal performance, but now the embodied carbon is a huge part, and it's coming through the TGS and other green standards across the country. We're going to be asked to be accountable for the amount of embodied carbon in our buildings. And these are the kinds of analysis I think all architects and designers need to be actually pushing their projects through continuously. And what we take away from this is, how do we build that better sunshade? How do we do it without those HSSs? And how do we actually reduce the carbon while achieving these results? So the second project that I'm going to talk about is a project called Limberlost Place. It's formerly called the Arbor for George Brown College. So the Arbor was procured through an international design competition. We were lucky enough to be the winners, working in collaboration with our JV partners, Acton Austria Architects. Just briefly, all of the names on here, shout out to MJM, my old firm, but also good friends. MJM and the Pat Cows, Shigeru Ban and Brooke McElroy and Provence Charlois and Turner Fleischer were the other finalists. I mentioned the pairings because the wood expertise was simply not here in Ontario. There were no Ontario firms that could have qualified for this project without Western partners or partners from abroad. That is changing, but at the time of this competition, we simply didn't have the expertise. We really need provincial programs to actually push timber forward. Our concept for the Arbor is based on this idea of breathing rooms. These are structural breathing rooms. Our structure is very thin and very flat. I won't have time to talk about it today. We have social breathing rooms. In a vertical campus, a teaching facility, the challenge is to take the social life of the building up the verticality of the building. So rather than having one central space that is ground floor oriented, we have many throughout the building. And we use these social breathing rooms to pull fresh air and daylight deeper into the footprint of the building. I'll take you on a brief tour of the building now, which is under construction. We have a basement. We will have a raft slab very soon. And the timber is due to arrive on site towards the end of the summer. We need some strikes to be over. So it's on the East Bay front of Waterfront Toronto, next to Sherbourne Commons and on Queens Quay Boulevard. It has an enhanced public realm. The Limberlost Place connects and engages with this vibrant community. The building is a 10-story exposed mass timber, tall, academic building that is achieving the Toronto Green Standards Tier 4 a decade in advance of the 2030 challenge. It is an approvals-heavy building that required 3 different alternative compliances, an expert team including PhDs, and it is on track to be the first of its kind in the world. There are a lot of other tall buildings that are happening in mass timber, but none of them are assembly occupancy over 10 stories. So we are in the most restrictive part of the code. What you're looking at here is the opportunity to bring students, the architecture students will be in this building from George Brown College, close up against the passive systems of the building. That is a solar chimney, a double facade, that is the passive engine of the natural ventilation system. The building has no central mechanical room, but has decentralized mechanical rooms with high efficiency ERVs on every floor, 2 on every floor, allowing the full volume to be used for the project, including the dramatic peaked roof. The peaked roof is actually part of the solar chimney that stretches up a full story and a half or 2 stories above the last floor that it serves in order to create that natural buoyancy to pull the air through the building. What I want to talk about today, then, is the fact that despite the fact that mass timber wants to be a compact footprint, one that is gravity loaded and very aligned, a grid that doesn't have a lot of deviation, but by carving out these spaces throughout this very regular grid, we were nevertheless able to create a variety of spaces for students. Communal spaces, cozy spaces, rising up through the building and giving students choice for the social life of the building throughout its verticality. And so this speaks a little bit to the structural model. I wish I had time to talk a little bit about it. There's huge innovation here to fasten up, but it is a very, very regular system, and it's also hybrid because we are using steel cores. So in achieving this environment, one of the things, even at the competition stage, we knew that we wanted to explore a prefabricated envelope. And we thought of this initially because what we wanted to do is we wanted to protect the timber as quickly as the timber is going up. All of the timber is essentially prefabricated, and it's going to click together very, very quickly. And what we want to do is protect it equally as quickly as it goes up on site. So at the competition, we were looking at that, at a prefabricated envelope. We then began to work through design assist with PCL constructors, Nordic for the timber and supply, Walters for the steel, and CGI for the envelope. And we explored a number of different systems. What you're looking at here is 8 inches of insulation, an R30 effective mock-up for the solid portions of the facade. This is an exploration using terracotta, a terracotta panel. Terracotta was eliminated, and we ended up moving to aluminum, not because of the cost so much, but because of the weight. Some of our panels were 2 stories high, and we were really pushing the cranes over their ability to actually erect these. There was also costs associated with possible damage in fabrication. So this can really only work working together in a design assist, really running through the risks and understanding where there are losses. So these are images of the facade, and shout out to my colleague Will Clausen, who actually produced this. He's out there. And one of the things that we looked at was that despite a prefabricated system, we could come up with different modules that could actually give some play to the facade. I'm going to move really quickly, but here's what it looks like in the natural ventilation mode. Air comes in through the windows, moves through a acoustic baffle into the hallways where it goes to the solar chimneys and is evacuated out through that natural buoyancy. In the hot, sticky summer and in the winter, the windows are closed, and that's when the decentralized mechanical system kicks in. The solar chimneys still work when the building is in cooling mode, and in the summer it creates a bit of an air buffer to insulate the project. We have an underfloor system that delivers heat and cooling to where the people are. I won't talk about that. So these are some of the targets we're hitting. Again, Tier 4 TGS, which is extraordinary. And we thought that this was how we could lay up the panels. So we tried to minimize the number of different panels, but the reality is when we started working with CGI, they wanted to actually incorporate the glazing into the panel. So we end up with more like 11 different types of panels. These are being mocked up as we speak. We are going on the 8th of June to Windsor to see the first mock-ups. An entire testing regime for air tightness had to be written specifically for this facade system in order for us to meet these targets. And so you start to see some of the different panel layouts. The panelization also extends to the curtain wall, which is a unitized panel system, and this is some of the curtain wall that's happening. But really, where the high performance of the envelope really works is because we're using what's called a chicken head detail at the top of the panels. So these panels are nested together and gasketed. And this is where the air tightness comes into play, and this is where we're starting to look at a panel that clips together. And we understand that CGI is as well pitching this system to other clients at the moment right now. But we've been working uniquely with them to develop this system. There are other prefabricated panelization systems south of the border. It's just getting more and more common here, and we hope to see it more. So that really summarizes my presentation, and I'm going to just quickly show you the timber system because we have to. 3 major components: a wide column, a slab band, which is very much like a concrete slab band, that spans 9 meters in just over a foot of depth. It is a timber concrete composite system. It has been subject to academic testing through the UNBC in British Columbia and Biberect University in Germany. We did a comprehensive testing regime for all of the connections, angled screws, a lug plate, and HPV. And we did an entire testing regime of 60 total tests. We tested the embedments, and we tested them to failure to the point where we now have strong data and have now advanced the performance and the understanding of timber concrete composite systems. That research is commonly available. It was funded. The project received $4.5 million worth of federal funding through NRCan. You can get those results, and thank you very much.
Cheers. Thanks. Thanks, Carol. Yeah, a couple of really fantastic projects. Carol, it's really, one other project in town reminds me of the partnership that you've got like with Integral and Transolar, and it's a TRCA project, another mass timber. And the values they're getting for their EUI are phenomenally low, getting down into the 60, 70 range, which really is heartening to see. So fantastic work, thanks. So next up, we've got Sudhir Bomo, who is an associate with Building Envelope at Arab. Welcome.
Hello. Great. Thank you for having me. I think this will be a nice transition from what Carol presented about sustainable facades and the unitization and the chicken heads. Today, I'd like to talk about, this is one of my favorite topics, talking about building envelopes and how structure and facade interactions happen, right? How the movements and tolerances between the structures and facade systems are coordinated, how they are conveyed to the contractors, and how we'd like to give a lot of emphasis to this topic, which we feel is oftentimes sits in the gray zone of the industry, right? Like who coordinates it, who's responsible for it. Yeah. So a quick snapshot of the pictures of the foot projects I've been working on from the past 10 years. I'm associated with Arab. I've been here in Toronto for the last 3-4 years. Had an opportunity to work on wonderful projects with really creative architects and a great number of collaborators across Europe. Each of this is a great story. Like if we start talking through these things, I don't think I have that much time today. But I really had an opportunity to work on various varieties of systems, and today I want to sum up all that and bring into this understanding about how structure and facade systems move and interact together. So who are we? We are Arab Building Envelope Design is a group within Arab, multitude of disciplinary practices, and we are around 300 people globally, and 20 plus people in North America, between Toronto, New York, and LA. But there's 300 people around the globe. We are connected with this really good network where we can tap into resources from across the globe. Why do we need joints and cladding? And that's really the topic that I would be covering through, right? It's really for facilitating for installation and transportation, and to allow for movement and tolerances in the system, and to provide separation between envelope systems. This is one of our recent projects, the Statue of Unity in India. which is worked out from our London office. I personally did not work about it, but this is a very fascinating project for me. Till date, most of the statues have been these super welded structures, and this is so huge that we can have the entire skin welded. We had to allow for a number of movement joints. The location is a seismic region, and it's 100 times as tall as me, 182 meters tall, and really huge panels. What you can see there is 5.5 meters by 6 meter tall and wide panels, pre-fabricated, assembled on site, and lifted up, installed on this superstructure. Absolutely everything moves, and we need to accommodate this in joints, and that's absolutely critical to get a successful project, right? I think this is where everything sums out to, right? It's important to understand that all non-load bearing envelopes have to be isolated from the movements of structures and thermal expansions and moisture expansions. If not, the systems will be imposed to loads that they're not designed for, right? Some of the loads, some of the movements that occur from the loading on the primary structures are imposed dead loads and long-term loads after the facade is installed, for example, creep settlements, live loads on the structures, wind loading, snow loading, seismic loading, and a number of loads within the facade systems where you have self-weight deformations and the wind loads and the ice loads on it, thermal expansion again, right? So visualizing some of these things, right? So it's critical to see how these loadings will deflect structures and sway and reversals of these movements. This is one topic which we feel is often not given very important sight to, is how the attachments on the cladding systems have impact on the primary structure. For example, the wind loads and the ice loads and snow loads on the facade attachments as we design sustainable buildings with a lot of louvers. So these loads will have to be coordinated with the primary structure engineers, right? They will transmit loads through which the facades will move more, right? So that coordination is absolutely critical. So if you look at a detailed analysis of what happens when in the process of the construction and installation of facades, some of the deflections that happen while construction, the short-term deflections happen prior to the facade is on site, and these are oftentimes considered as movements and tolerances by the contractors. And there are movements that would happen as we install facade, and they can be adjusted sometimes depending upon the system at the brackets, and their whole building life cycle, the remainder of the movements that happens throughout all these loads that we discussed will need to be accommodated in the joints, right? Joints, as much as we like or dislike, they do a lot of functions. They're important for transmission of forces, accommodating movements, accommodating tolerances. It's important for them to be durable, resistant for birds or animals not to get into it, sometimes be thermally conductive, electrically conductive, and sometimes not. Sometimes they're important to be fire rated. So there is this enormous suite of important things that go into these joints, and one has to think about during construction. And when things go wrong, things are not as pleasant, right? So we have seen in projects where like glasses are falling down because of insufficient accommodation of thermal expansions, for example, right? We don't want to see these in projects, right? So for example, in this case here, the head restraint is not sized enough to take care of the wind uplift on the roof, right? As a result, in a wind event, the window disengaged from the structure. So that's, I mean, a lot more examples if you look at it, right? And summing up these things, right, it's really like buildings and facades move, and no two buildings are alike, right? If you not ask you a structural engineer, right? So there's no two building alike, and not all the systems, pre-designed systems will work. So it's absolutely important that every facade system has its own way of accommodating movements, and every facade system has their own limits on how much they can accommodate and how the mechanics work, right? So early collaboration is really key for getting this sorted. So I'll be talking through a couple of examples like stick and unitized systems to generally explain how the movements are taken care of, but these principles do apply to opaque wall systems, stud wall systems as well. Again, stick systems are the ones that are not prefabricated. You bring mullions as sticks and assemble them on site, bring glazing, and do either cabbed or SSG system on sites. And unitized systems is where you have your entire prefabricated and interlocking sections that allow for movement. Some of the components of the stick systems, and I'm sure everybody here is very familiar with stick systems. And that tiny gap between the glass and the screw head is really where all the movement is accommodated within the mullions. And similar to that, on the transoms as well, there's a gap where the movement gets accommodated. And things change slightly when you're using stick system on a multi-story building where you have to allow for slabage deflections between levels. And a quick graphic kind of showing you how the glass that is glazed into these systems is accommodating these movements, right? For example, from going from the originally installed phase all the way to as the mullions displace vertically, you see the glass would start rotating along with the mullions and then would start sliding after the rotation capacity is exceeded and first contact with the mullion is made, and they get squeezed in between, right? We really don't want glass to be interacting with metal without designing for it, right? When you see these, you need to allow for a non-metallic element that can take care of the glass to framing connection. These are, and within Europe, given the number of times we get into this problem, Ed Forward, one of our director colleagues who steers our digital innovations, developed a number of tools. I'll be talking through some of the tools that we use in coordinating this. This is a visual tool that kind of explains the architects and the structural engineers how the impact of, for example, in this case, you're seeing how when the upper slab drifts, like that's when your first mullion to glass connection would happen, and you see the sagging of the slabs, then further exaggerating these problems. And when they both happen together, you'll have to make sure these load combinations are considered in designing that, right? It's important to keep in mind the load reversals as well. Oftentimes, we don't get this sort of information from every manufacturer, but there are documents out there available for expressing how much the system can be subjected to movements, right? For example, here, this is a Schuko 50+ system. You can see the gap between the glass to the frame is only 5.5 millimeters, and they can only allow the glass and frame to get as close as 3.5 millimeters, right? Not really anything if we look at the primary structure, how much it could move, right? Again, like there are charts out there that kind of give an understanding of how aspect ratio will influence the allowable mullion deflections, right? And the wider systems, of course, will allow for, this is a wider version of the same system. You can see everything in the wide there is placed where we don't have concern. But as you look at the aspect ratios of a taller panel and narrower, taller panels, we'll see a larger impact of glass to frame interfaces. Quickly running through unitized systems. Hoping everybody here is familiar with these systems, like interlocking systems manufactured in shop, comes to site as units and get assembled together. And there are a number of varieties of unitized system. Everybody likes to do it their own way. And there are systems that have gutter splices, which bridge two units together in the horizontal section. And there are systems that have these swords, which are also used as lifting lugs for installing these panels, which are most of the North American systems. And they interlock with the vertical section for the panel above. And these both systems move very differently. And this is, again, a quick visual tool explaining how the different systems work. For example, we're looking at slabage deflections, of course, exaggerated, right? We are seeing the panels kind of open up when the floors are subjected to loads. And when you combine this with the drifts, and this will be another complex problem to deal with. And this is how, for example, a system that does not have a sword between the vertical mullions would behave. If you look at a hung and sworded system, it moves very differently compared to the one before, right? And this would mean a lot different for how the gasketing works and how the air tightness of system is impacted. So on every project, we go through this process of establishing all the movements that the slab edge is seeing and the facade anchors are seeing. And we work closely with the structural engineers to coordinate load combinations that these joints should be sized for, right? We talk about load combinations of designing buildings, but really, when it comes to joint sizing, it's really, you either rely on your previous project, say this is the joint we used and we'll go with it, or you take one of the component, for example, live load deflection, but then not every other component, right? So it's important to have these combinations studied before you finalize the joint sizing, right? Some of the tools that we're using, like use Grasshopper pretty heavily in this exercise to coordinate the deflections between structural engineer. This becomes extremely important if your buildings have either uneven loading or shapes that, for example, have cantilevers or buildings that are not, I don't have precedent to bring it. These are all confidential projects. I can't project some images I would like to. This is one project, for example, you can see where the core of this building is eccentric. So it's aligned to the left of or the right of the screen. The straight edge is where the core is. And the columns on the other edge are all inclined. As a result, the deflections are not typical. And as the facade is being installed, the core has to be post-tensioned to counteract the installation of facade and lift up or get the geometry right as the construction is progressing. The analysis that you're seeing here is the interaction, different joint interactions between two panels as they come close or forward to get or go further apart at every corner, right? And if you can see here like the difference between how a gutter splice system or a sorted system would work, right? For example, the dimension C, or the panel opening, is the worst case joint that a splice system needs to be designed for. And a solid system needs to be designed for the dimension B on the screen there, which is where, for example, if you're using a typical North American system, your continuous rain screen gasket or the air seal gasket are the ones that will be pushed vertically stepping there, right? So if that seals break, there's no way to access and maintain these, so it's important to get these tested, right? What you're seeing here is a different load case comparisons. So every joint is seeing its worst, for example, worst case at a different load case. So it's important to understand the load case and the sequence of installation as we model these things. Right? Much more newer tools. We're all used to doing like BRIM 360, and Speckle is a slightly different version of coordinating information between architects, structural engineers, and other players. So here we're talking about databases and where you store geometric information about the project, and the structural engineers does their analysis and sends a similar data stream for the facade consultants to analyze those and see how the glass panel joints are working. And these are very critical when we're working on complex projects or projects that are not very regular, right? And these tools allow us to go from this offline design journey to be very proactively managing all the discipline input into a streamlined flow, right? This is a small workflow that shows the interaction between the workflow that goes into sizing these joints. You take your panelization from the architect, and the structural engineers does their analysis, and there is this coordination happening between the facade consultants and the facade contractors for coordinating the load cases, the positions of these nodes, and how the glass and substructure weight, and movements and tolerances, of course, and they all get together into creating a package that is coordinated between structure and facades. Right. So why is this important? It's structure plus skin really takes the major share of embodied carbon on projects, and it's long-lived, and it occupies a lot of cost. And when we start over-designing, for example, you over-design your slab edges, then you're creating a lot of embodied carbon in those designs, right? At the same time, if you let your facade joints do more, or your facade mullions be wider, you're at the same time doing the same thing, right? So it's important that the coordination is key for getting to a sustainable project. Some conclusions. The system selection aspect ratios are really key to for getting the ability of the facade systems to accommodate these movements, and facades are big cost drivers. Discussion on movements and tolerances early on is best, and it's important to understand the construction sequence of projects and look at different load combinations and establish the worst case joint sizing. Important to consider load reversals and seek the input of facade consultants for coordinating these conversations. And do not underestimate the flexibility at the slab edge, and take time in coordinating these values. And hopefully this makes us build projects that are more compatible and don't have the incidents of falling glass from projects. Thank you.
Thank you, Sudhir. That's fantastic. I love the connection between the previous presentation when they're looking at curtain wall on a mass timber building, and those movements become even more exaggerated when you get into an organic substance like mass timber versus concrete and steel. So awesome work. Thanks. Dean White is up next. He's the regional facade sales manager for Cosentino North America. Welcome.
How's my volume? Is it good? Perfect. Well, thank you for being here today, and I'm privileged to present in front of you. A little bit less technical of some of the things you've been seeing today. I want to be introducing you to ultra compact surface and our particular brand of it. I talk about how it can be integrated into facades and curtain walls, and just give you some practical things to think about when you're designing with this type of material in your facades and in general with facades. So we'll talk about sustainability up front real quick because it is a very important topic. We'll look at what is ultra compact surface, how is it made, what is it actually, and then look at the facade applications, curtain wall applications, and look at a couple case studies. So I've got 15 minutes, so this is going to be, like we say, down and dirty, right? I want to talk about sustainability first. Obviously, it's a very hot topic, a very important topic, and at Cosentino, we take it very seriously. Our facilities, we've got about 10 million square feet under roof in the south of Spain that we manufacture a variety of hard surfaces out of, including ultra-compact surface. And all the electricity we use in that facility is renewable. It's all wind and solar. We recycle 99% of the water that we use. It's the south of Spain. It's where they filmed all those Clint Eastwood spaghetti westerns back in the day, so water's like gold. I'm from the Yukon originally. I know the value of gold, but over there, water's like gold. So it's a really key initiative that we have. Also, our factory is highly automated. So the production line for ultra-compact surface, and we have two of them, are 1 kilometer long each. And in that factory, you only see 10 to 20 people working because it's all automated. It's all roboticized. We move the material around with robots. It's very efficient in the way it moves, so we keep our emissions down and we keep our energy consumption down and our carbon footprint. And then we offset the gas that we use in our furnaces with projects locally and around the world so that our production lines there and the material is carbon neutral from cradle to grave. So it's very important for us. And without getting into more discussion about sustainability, that's sustainable manufacturing side of things. We're also looking at how do products and how do our products impact the social aspect of sustainability. Is it something that's socially sustainable over years and so forth and so on. So very important. I just wanted to of course, support that move towards sustainability. When we talk about ultra-compact surface, it is a material that's formed from inorganic minerals that are mined from the earth. So they go through the metamorphic process for a few million years. We come along and mine them. We powderize them. We combine them in different combinations to get different colors and patterns and so forth, so different recipes. And we put them back through the metamorphic process is what we do. So it's really ultra-compact surface. You can think of as an engineered stone or a sintered stone. You might hear some people call it a sintered compact surface. It is a very dense product. When it goes through this sinterization process, that is a process that involves temperature and heat. So, pressure and heat, very high pressure, 25,000 metric tons a slab gets pressed under, and then it goes through the process, gets decorated, et cetera, and then goes into 300-meter long ovens, gets heated up and cooled down. And when it's cooled and finally in its final state, it's all bonded at the molecular level. So what you've got is a material that is very dense, has some very unique physical properties that allow it to be used in many different applications from the interior to the exterior of a building. And we'll talk about the uses on the exterior here. The physical properties, one of the most interesting ones is the UV stability. So when you see the colors and patterns around this type of product, They're very, very durable. They're not going to break down over time. They're not going to scratch off. It's a very hard product. It's 7 on the Mohs scale. So you can take a chainsaw to it, mark it all up, and you're going to see, oh, look, I did a bunch of damage. You're going to wipe it off with a cloth, and it looks like you never even touched the product. So very durable, very UV stable. It's non-combustible. When you're using it in a ventilated facade or a curtain wall type application, you need to put a fiberglass mesh on the back of it that's attached with an epoxy. So when we did our fire testing, we used the CanULC S135, which is commonly used for composite materials, because it's not just the ultra-compact surface that we're testing, and it's a non-combustible product. Without jumping into all different kind of certifications, this type of material has been tested with Miami-Dade type systems, NFPA 285, a bunch of different systems, and we have, you know, ICC and all kinds of certifications worldwide, so those are available. And most manufacturers have that same type of thing. The product is very non-porous when it's formed, and that provides another unique characteristic, and that is graffiti-proof. So if someone puts graffiti on it in the urban environment, you can wash it off with soap and water. You could use harsh chemicals if you want, because it's not going to impact the material itself. It's very chemical resistant, but you don't have to. So it's not a treatment that you see with other materials that may discolor the material when you treat it, or you have to repeat the treatment over time. It's just a feature of the physical feature of the product. Very low coefficient of expansion, very non-porous, so very, very low water absorption. Freeze-thaw proof. It's not going to spall like a natural, stone. It's not going to break down over time. It's relatively inert. It's not going to be the thing that's expanding and contracting on the building. It's going to be the subframing. It's going to be the substrate. It's going to be the building itself that's moving. So you still have to design with your gaps between panels and so forth. But to know it's not the material itself that's moving, it's what it's attached to. Large format, which I'll talk about in just a minute in more detail. Very dimensionally consistent. So the manufacturing process is highly automated, highly controlled, very high quality, and across that slab, which is 56 by 126 inches, it's the same gauge all the way across. So unlike, say, a porcelain where it may get thicker in the middle and thinner at the edges, it's dead flat and the same gauge across the entire slab. Abrasion scratch resistant, I mentioned already, it's 7 on the Mohs scale, so it's diamonds and such. You got to use diamond saws to cut it. And the maintenance is very low because of the low porosity. It has a very long life cycle, so this gets back to the sustainability as well. It's not something that requires maintenance, okay? You may pressure wash it every now and then if there happens to be some dust collecting somewhere, but it is not going to break down over time. It's going to have a very long life cycle in the building, so your total cost of ownership is much lower than other materials where you're going to have a lot of maintenance replacement after a decade or 5 years or 2 decades. And then very durable. When we look at the size of it, it's a large format panel, and it's 1,440 millimeters by 3,200 millimeters, or for us old guys, 56 by 126. Comes in a bunch of different thicknesses, 4 millimeter, 8 millimeter, 12, 20, and 30, and depending on the application, you're going to select the thickness, depending on what kind of application and attachment method you're using. And it's a relatively lightweight product. So from the 4 millimeter being just over 2 pounds per square foot, the half-inch 12 millimeters, 6.5 pounds per square foot. The 8 millimeter, 4.3, and 8 and 12 are the most commonly used for rain screen and curtain wall applications. A lot of different standard colors, 60 plus and more being added all the time. A lot of facade-friendly colors as well, and recycled content within those colors. So the minimum we have on any one is 5%, but some of those colors have 80% recycled content in them. So another back to the sustainability view. You are able, with most manufacturers in this type of material, you can do custom colors. As you know, with all kinds of facade materials, you can do custom things if you hit the minimum requirements, depending on what the manufacturer says. With us, you can do custom from scratch for 35,000 square feet, but if you're taking something that's existing already, say one product's got a color and a finish, and another one's got a different finish, you're combining existing things, then you're looking at a 10,000 square foot minimum. The thing is that pretty much everything is doable if it meets the requirement. applications. There's really 4 of them now, and it's getting interesting all the time. Obviously, it's going to be used in a rain screen application, curtain wall for opaque areas, unitized wall, the old standby for some smaller jobs where they might direct adhere it. But also, there's been quite a bit of interest. I travel North America and from the precast community where they've been skinning with natural stone and so forth, where they skin also with porcelains, you know, granites, limestones. They also look to skin with ultra-compact surface. And everybody does their thing somewhat different, just like in the curtain wall world, but it is being used in those applications more and more. This next slide is, I don't expect anybody to read that, but it looks like it is readable, is really just to show you the spectrum and the flexibility of the product and how you can get it on a facade. Okay, so starting on the left, we're looking at more inexpensive, budget-friendly type applications, all the way to higher performing applications on the right with a bunch of different budget ranges you can hit. So you've got, you know, visible, you know, when we're starting on the left, you've got visible clips, kind of like a mirror clip. When you're looking at next long face fasten, which you see often with, you know, high pressure laminates and fiber cements, you can do that with 4 and 8 millimeter ultra compact. Chemical bonds, so structural adhesives. Now, there's a couple different ways, obviously, that gets applied. There's field applied, which isn't necessarily my favorite way of using adhesive because you're subject to temperature, humidity, dust, workmanship, quality control, basically, right? If a guy's working up on the swing stage trying to apply structural silicone, that's a lot different than doing on a table in a controlled environment. So very widely used in controlled environment. The structural silicones are the same type that you use in glazing. You know, all the normal suppliers have compatible material. Kerf or groove, that's you see that in stone quite a bit, but you also see it with ultra compact surface where there's a groove put in the top and the bottom of the panel and mechanically attached back to the verticals on the wall. When you're looking at, you also have honeycomb. So we've got honeycomb partners. We've got one of them in the room here today, Cladify, who put honeycomb on the back of their on the back of our material. Quite widely used. Obviously, you've got some structural strength when you're using that, and you can do some complex geometries and deliver panels that have complex shapes that can be installed all at once instead of as separate pieces. All these systems have their pluses and their minuses. Undercut anchor, Kyle anchor, or Fisher anchor, very widely used in large panel materials. That's also used with ultra compact surface. You can use it from 8 millimeter up. So now you can use an 8 millimeter Kyle anchor, which is a 4 millimeter anchor with 8 millimeter thick material. So that's very widely used. We have a lot of partners that supply that across North America. I know Blair is here from Facade Systems, and they represent Yukon and Telling, and they have a bunch of systems that use that type of attachment. And then pressure equalized. So the pressure equalized is a system that is similar to an HCM system, perimeter frame, and you've got the ultra compact surface that is attached out with structural silicone. And in Ontario, you'd be familiar with Ontario Panelization or Elemex to do that type of system. But there's different people across North America that do all these systems. And what I was just trying to exhibit here is the flexibility of how you can get it on the wall in a ventilated system or a unitized. And we'll talk about curtain wall here momentarily. I don't expect anybody to read that, but we have a full facade manual for all the different attachment methods. And this is one of the very useful pages that says, if you're using that system that's on the left, which has a generic name, and you're using that thickness of material you see across the top, then you've got red and you've got green. So stop and go. You see green, that means go. You see stop, it means you can't use that thickness of material with that type of attachment method. And then there's some basic parameters there as far as slab panel size and so forth that you can do with each one of those. This is very typical for other people that make sintered materials as well, that they have this variety of attachment methods. On the curtain wall side, this is a really exciting focus for us, obviously because getting involved early in the design assist, getting material selection early is key in getting your products on a project. So that's really key to us, and we've got a set of typical details of how you can glaze it in a traditional captured system or SSG system, and also a unitized system. So there's a lot of ways to integrate it. It's very similar to glass, has similar weights and thicknesses, so curtain wall contractors find it easy to work with and easy to integrate into the opaque areas if they're glazing it in. And of course, we'll talk, I'm going to show you an example of a unitized wall shortly. It's really important for us to understand when we're doing a facade what material we're working with, what size does it come in, what slab sheet size, whatever it happens to be. How do we reduce and optimize the cost of the panels that are going to be fabricated and installed on the wall? So there's a few key things to understand, and it's not new to any of you. One of them is if you got whatever your blank slab is, if you throw away 20% of that in making a panel, you're going to pay for that 20% in the construction of that panel. You're also going to negatively impact the sustainability part of the manufacturing and getting it on the wall because you've created waste, when if we actually planned ahead of time and design assist and optimize the panel layout, we could reduce that waste and reduce the cost. So that's really key. Doesn't matter what the material is. The other one is panel size. So panel size obviously impacts, because the smaller the panels, the more attachment points you're going to have, the more framing on the wall. It'll drive up your dollars per square foot considerably. More labor, etc. The waste I talked about already, but the panel complexity is another thing that impacts the cost on these type of products, these type of panel products where you can have mitered corners and so forth. If you look at a mitered corner, typically they're $6 to $6.50 or $6 to $7 per square foot to do a miter. And you have to understand the costs and have that transparent discussion up front when you're designing the building. Say, where do you want mitered returns? Where is it important to have those mitered returns, and what's going to be the impact on the cost of the project, so that you budget properly and you start comparing apples to apples. Not only numbers, but the style of miter and the complexity of the panel itself. How many miters? Because I've seen pressure equalized panels that had 7 different returns on the same panel. So that adds to the complexity. When you're working with manufacturers like ourselves that make these products, we will do a facade study, help optimize the layout, because we're going to go through that anyways when someone asks for a budget or they send us something to quote. We need to go through and do that layout so we can calculate the waste and we understand how to price it. So we're going through that anyways, and the earlier we get involved on the design assist, then the smoother it goes all the way through the process, and there's no surprises about dollars per square foot. I'm a big proponent of being very transparent up front and talking about not only the material cost, which you'll see some manufacturers say, hey, this is our material cost. That's not the cost of putting that material on a facade. I think we all know that. The fabrication costs, the subsystem costs, the labor, the on-the-wall cost is what's important, and comparing apples to apples. So the more transparent and earlier those discussions are, the better off everybody is. I'm going to look at a quick case study here. This is the Cap West project in Munich, and this is a unitized wall project with 135,000 square feet of ultra compact on it. And you can see what they did here from these photos. So they created their wall units, and they have these horizontal frames on their wall units. You can see the ultra compact surface in the second picture from the left. That is very clearly indicating the mesh on the back, so you can see the mesh. Those are Kyle anchors, undercut anchors that are holding those clips on. And then those clips will go, if you look at the far right, you can see them hanging off the horizontal framing on that wall unit. And then, of course, you know the rest. It's combined with the glazing. It's stacked on site. And you go for, you're really controlling your on-site construction schedule, which is key. When you're looking at your project and the installers and the curtain wall people, there's lead times when you're getting these products. So you could, say, order stuff that is fully fabricated, holes drilled, etc., and it's going to have a lead time of 8 to 10 weeks or 10 to 14 weeks, whoever the manufacturer is, wherever it's coming from. But you may not have site dimensions. Typically, you're going to want site dimensions before you start fabricating these panels, right? But you may not have those, so you may fabricate some typicals and leave some off on the ends and maybe make them larger and cut them down, or you may work with a local fabrication partner that will cut them down for you so you have slabs on hand and you have better control of your construction schedule on site. So there's a lot of different ways to go about delivering a project, and minimizing the impact on construction schedule and costs. I pulled this one up. This is a Charles in Atlanta because one of the things that I preach, okay, I'm done in 2 seconds, is that don't get boxed in of thinking of one thickness and one attachment method on the same project, okay? Look at the project, depending on what the scope is. You can use different thicknesses, different attachment methods on the same building. This one actually has fully adhered at that entrance in the middle picture, open joint Kyle on the other picture on the left, and running up the tower itself. I'm going to fly through one more example here. This is the Toha project in Israel. A real interesting project with 300,000 square feet of ultra-compact on it. There's 11 different colors, 6 of them custom, and this building is flipped on its head. At the bottom there where you see the ventilated area, that's actually the mechanical area. You can see how the panels were installed to allow ventilation, and a great, a graduated spectrum of color running up the tower. This type of material is used interior and exterior, a lot of applications. This is Rafael's Academy in Spain. You've got cladding, you've got pool, you've got pedestal deck, you've got countertops, interior flooring, interior wall cladding, and the facade, of course. So very flexible product, and we'd be happy to talk to you about it all week long. Take care.
All right, thanks, Dean. That's great. Good to see a really durable, long-life material out there that we can use on our tall buildings and modern structures that will have a long, long lifespan, getting into the 60-year range, I'm guessing. But up next, we have Tomar Diamant of Teeple Architects, Principal.
Thanks, John. Hi, folks. Okay, 14 minutes. Okay, I'll be very quick then. Okay, so hi everyone. By ways of a brief introduction, Teeple Architects is based here in Toronto, founded by Principal Stephen Teeple in 1989. We're about 32 years old, about 30 people, and one of our core areas of practice concentrates in higher education. We've been involved on college and university campuses all over Canada, and as you'll see today, most recently also in the United States. So today I'll be focusing on 2 specific projects, the Science and Technology Building in Langara College in Vancouver, and the Calvin and Tina Tyler Hall Student Services Building at Morgan State University in Baltimore. Both of these buildings were conceived of as campus gateway buildings, and both projects, while being very different contexts, obviously, both of these projects amalgamate a diverse programmatic range on sites, quite challenging sites actually, situated at the edge of campuses that had over the years grown somewhat disconnected from their surrounding community. So at their core, both of these buildings are very much about reconnecting, re-engaging with the public realm and inviting the public into the campus. It's also worth mentioning that both of these projects really benefited from early involvement with CM pre-con services that also included bringing lots of very talented and dedicated trades and suppliers to the table in a highly collaborative process. So Langara Project approached us with a really tricky problem to solve. They knew they had resources to mobilize around one big capital expansion building program for the foreseeable future at the onset of this project. They had one specific site in mind. It's a commuter campus, but fairly contained. One specific site that they had earmarked at the campus gateway at the northwest corner, and a lot of building program for it to accommodate, frankly, too much program for such a small site. So the building involves the consolidation of the student services and administration spaces, but also it needed to satisfy a desperate need for laboratory and instructional and faculty space for its science and technology programs, which were bursting at the seams. So as you see here, the building cantilevers above a campus entry roadway, and that's frankly just our approach to solving the site problem of having too much program for too little site. but also conveniently a means of accomplishing this, this somewhat memorable, unusual campus entry gateway condition. It's worth noting also that immediately across from the campus entry roadway, which is also the main fire truck access route, immediately across in that open field, there exists quite an extensive geothermal field, so it was absolutely non-negotiable. We couldn't touch down across the road with structure, so we said, ah shucks, let's just cantilever the upper 3 floors, 16.1 meters. So that was kind of fun, obviously a very tricky structural puzzle to solve. And part of the equation, obviously, a big part of the equation was the building envelope. And the strategy here, which you can see in this image, was to take the upper 3 floors, the laboratory science and technology floors, to stack the labs, the lab modules, to minimize vertical runs from the fume hoods, and to stack them efficiently and contain them within the large 3-story trusses that are required to achieve this cantilever. But also it was important for us to kind of gather them behind this somewhat fuzzy shroud of louvers. Early on in the project, we kind of envisioned this louver system, both as a means of achieving some very important performance requirements, which I'll touch on in a second, but also importantly, to kind of unify this levitating mass and play up the bravado of this structural cantilevering feat, but all in the service of creating this gateway gesture that Langara really wanted to achieve. So from a performance standpoint, with quite deep floor plates, these louvers evolved also out of a consideration to modulate the light, as I said, to bounce and refract diffuse daylighting as deep into these floor plates as possible, and also to mitigate glare. Another piece of the sustainability puzzle that you can see in the section and the photo is returning air passively by means of a full height light well that also acts again to wash light deep into the floor plates on the upper floors. So I wanted to include these pictures to give you a sense of the experience from within the building, the diffuse light condition in one of the labs, and also the circulation spaces at the perimeter of the upper floors. It was very important for us to strike a balance between what we wanted to achieve aesthetically and from a performance standpoint, but also to achieve a louver density that would never feel cage-like or constraining or interfere with views, including views to the mountain from one of the sides of the building. So we cast a fairly wide net early in the design process, and we looked at available louver facade systems, but both because of their costs being beyond our modest means, but also due to some lack of variability and customization, we approached our friends at Engineered Assemblies with the idea that it might be more economical and more flexible to cobble together a system from more or less off-the-shelf, readily available extrusions, aluminum extrusions. And here on the left, you can see an early plan detail showing how we thought that system might come together. Essentially, one-story cassettes that would be shop-assembled, louvers in various orientations and spacings, that they would come together sequentially, one cassette nesting into another, both supported on each end by intermittent vertical HSS that would then in turn be supported off of slab edges through thermally broken detail through the building envelope. So Engineered Assemblies built this mock-up for us and began collaborating with us and our CM quite early in the process, as I mentioned. Another great advantage of the strategy of decoupling the louver system from the building envelope was that it enabled us to really shake some money out of the actual building envelope, importantly though, without sacrificing on thermal performance. So here you can see also in kind of early mid design development, the envelope really starting to take shape, and we were proposing corrugated metal siding, a face-fastened, inexpensive corrugated metal siding, rain screen supported on thermally broken clips, and a heavily insulated facade. I think that's 150 mil of outboard insulation and about 3 millimeters inboard. And I should go back just to touch briefly on the fact that I think so as I mentioned, collaboration was ongoing, and that included at milestone costings. I think it was about the Class B costing that exposed a real budget squeeze, and the louver facade system was at real risk of being value engineered out of the project. I think that was mostly due to, the increased cost and complexity associated with the steel structural system for the cantilever, just the sheer amount of steel and the complexity there, including the complexity of fire rating it. So we then began to question our initial assumption regarding the off-the-shelf, readily available extrusions being the best way forward, and engineered assemblies wound up informing us that it would actually be more economical just due to sheer material costs to pivot to custom extrusions, which we had always assumed was beyond our snack bracket. So these custom extrusions reflect what's actually on the building, and they represented, I don't have the number off the top of my head, but a significant reduction in material costs. Obviously, the budget was driving that, but there's a clear embodied carbon component to that decision as well. And ultimately, this process progressed to a point at which we locked down essentially a linear overall length of extrusions that we could afford for the building, and then it was up to the design team to create a parametric process by which we could distribute these lengths across the elevations, play with densities and orientations in a manner that reflected interior program requirements, window locations, and so forth. So you can see this color-coded image reflects, I think, one of the final outputs at the shop drawings phase to finalize the louver facade distribution. And here, close-up details of the end result, accompanied by some shop drawings that pretty much reflect our initial system, just kind of further refined. In red, you can see the red iron, the galvanized components, the intermittent vertical HSS supported on that T, which is a knife plate bracket, fastened through a 13 mil high-density polyethylene thermal shim through the slab edge trimmer angle through a grout pocket. And here's the system going up. You can see the knife plate connections installed at the slab edges. And here you can see various degrees of completion of this facade. In red on the right is another detail that was developed with the cladding contractor, Marine Cladding. And it involved these continuous reveal, this two-part break-formed continuous reveal, which allowed the knife plates to slot through there instead of through the actual cladding, allowing the cladding to be regular, panelized, no field cuts, nice and clean, especially important given that it was a fairly kind of rough and ready approach to begin with. And here the end result on the left, like very much achieving the initial design ambition of having these upper three science floors unified as this levitating kind of gateway mass. On the right, you can see this is kind of the most public corner of the building, and you get a sense of how the louver density starts to dissipate as the program opens up. What's actually happening on that corner of the building is that there's a three-story oculus, a structurally glazed sculptural oculus, around which there's a communicating stair. It was very important from the earliest stages of planning this project to kind of counteract the striation of the science disciplines among the three upper floors by introducing some kind of vertical social element. And when we showed this project to the CM early on, to their credit, instead of laughing us out of the room and telling us we couldn't afford it, they took it back, thought about it, and they basically informed us that they thought that because of the sheer amount of steel on this job, that if this was fully resolved, carefully detailed, engineered, we knew exactly what we needed and we drew it super accurately, we could sneak it into the miscellaneous metals tender, and it would probably benefit from an economy of scale and not be that big a deal. So that was a really significant insight that allowed us to achieve something we kind of half-heartedly thought would always get value engineered out of the thing at the end of the day. And yeah, so we worked with Glass Tech, a really great glazing contractor out in Vancouver, to figure out, you know, a fairly basic veneer application on a steel skeleton cage. And there's the end result. I think I'm running a little low on time, so I'll breeze a bit more quickly through this project. This is in Baltimore for Morgan State University. We are honored to be invited to work on this 150-year-old campus. It's Maryland's oldest HBCU, historically black college or university, in this case a university. As I said, 150 years old, and on the left of this image, you can see the original historic quad, which is very neoclassically planned. And across the road, the modern campus, which is oriented along the Morgan Commons, and it's lined with an assortment, a somewhat hodgepodgey assortment of more contemporary buildings from, you know, decade to decade. So the site itself was tasked with creating a transition between the historic campus and the more modern campus, but at the same time also bridging the sectional divide. You can see that bridge that crosses the road and stitches the two portions of the campus together. That bridge is the actual level at which much of the campus is situated, including the Morgan Commons and the Quad, and the surrounding neighborhood is a full story below, which creates this kind of separation between the campus and the neighborhood. This building was, as I mentioned before, was all about inviting the city into the campus, so it was very important to plan a building that ameliorated that grade change in an accessible manner. And here I'll show very quickly the existing context, the campus buildings of the historical Quad, and also the modern campus on the bottom, really have this unifying element of this Maryland field stone. So having a stone building was pretty much a non-negotiable point for the university, but at the same time, they had this also this strong desire for an architectural expression that was very forward-looking, dynamic, contemporary. And so from day one, the struggle for the design team was really how to achieve you know, a stone-clad building that's connected to tradition and history, but at the same time dynamic, forward-looking, all of that. And so a highly iterative, collaborative process with our partners, GWWO in Baltimore, resulted in a site approach, a site strategy where these sweeping curves define the south and north faces of the building. To the north, the building sweeps in, it sweeps out to kind of embrace the surrounding neighborhood, but also creates this welcoming forecourt, arrival space, and at the bottom, at the south, the building has a reciprocal curve that responds to the prow of the existing recent library, library building. And on the right, the building is held back to preserve an important view access to Holmes Hall, which is the oldest building on the campus. So after establishing that basic strategy, we kept looking for the right architectural expressions. This, I think, was a late-night sketch that Stephen Teeple left on my desk halfway through schematic design, which really set the course for a design approach that saw the building as this kind of unified stone volume with these sculptural moments, these cuts, that occur at public spaces within the interior program. So also the CM, Barton Mallow, through a target value design process, informed us very early, and we were part of this decision-making process as well, obviously, but we realized very early that stone veneer precast was likely the only way to achieve a stone building within the budgetary constraints of the project. Now, we love precast. We don't love everything about precast, embodied carbon, obviously, but it kind of became a given, just a condition of the project that precast had to be embraced in order to achieve this non-negotiable requirement for a stone building. So we worked within the constraints of precast and the opportunities of precast to really achieve some relief within the facade, especially portions that required a more regular punch opening approach. So we created this relief pattern to add a layer of texture and dynamism to the facade, but also to counteract the perception of legible, legible vertical panel joints, you know, to kind of avoid that precast aesthetic. And we also, from day one, paid very close attention to stone coursing, and the stone itself. The search for the right stone became an important part of this, the facade design, and frankly, it took a long time. And this kind of elliptical process, after looking at Nebraska, the Middle East, further afield even, we kind of circled back to our backyard 3 hours north of Toronto in Owen Sound, ledge rock or Aramosa limestone. And this, the uncharacteristic or the unusually dark hues really complemented the tones found on the Maryland fieldstone and really spoke to the client. And then there was quite an extensive process of testing the right level of polish and grit to achieve the right tonal range, and also to kind of understand the natural lightening up process that occurs when it's sitting on site. So this involved a mock-up, an early mock-up, so that we could really understand how quickly and how much the stone lightens, so that the tint on the precast concrete surrounds could really be carefully calibrated with the end objective of everything kind of leveling off around the same tonal range. So again, early mock-up, so important. This process continued. Ultimately, you can see a finished panel in the precaster's yard right after being poured. Quite a significant color difference between the precast surrounds, but in the field, things really did level out as planned. Very constrained site, limiting staging areas, so production delivery had to be like meticulously scheduled with the contractor, and the pour schedule and the install schedule was extremely tightly controlled by Barton Mallow, and that stretches all the way back to the procurement processing of the stone as well. I think I'm almost done here, so I'll just breeze through some photos of the end result. This is the arrival forecourt to the north of the building. This is really kind of like the arrival point onto campus. Now you can see the outside portion of an inside-outside stair, this kind of carve into the building, this welcoming entrance on the ground floor. Some sharp prismatic metal returns, and some sneak peeks of the interiors, the inside component of that inside portion of that inside-outside stair, the ascent from the lower level to the upper level of the commons, and also a peek at how that exterior formal language manifests on the inside, where a flowing wood soffit provides intuitive wayfinding, gently guiding students through the building up into the student service hubs. Thank you.
Thanks so much, Tomer. That's great. I really love the collaborative approach that you had with the contractors. It sounds like a really fantastic integrated design team, and came up with some really great projects, so congratulations. Really great stuff. Next up is Michael Andres, who's a market development manager for Eastman with an exciting new product.
Can everybody hear me? There we go. That would be good, thank you. Well, good afternoon, everyone. It's a pleasure to be here to talk to you this afternoon about a new bird protection solution utilized in laminated glass for the architectural design community. It is SafeFlex FlySafe 3D is the product. Today we'll go through a number of different items, the first being just a little bit more about SafeFlex. We'll talk a little bit about the emerging drivers that continue to push this specific issue to the forefront with regard to bird protection. We'll talk a little bit about and introduce the FlySafe 3D product as well. Why FlySafe 3D, the importance of it, the attributes, the benefits, and then why is it different from some other potential solutions that are out there on the market. So with that, just a little bit about SafeFlex PVB interlayers, high-performance PVB interlayers. SafeFlex itself as a brand has been around for over 80 years, started out in the automobile industry for windshield, side lights, things of that nature. Over time, it was then, in the 1960s, utilized for the first time in architectural glazing because they saw the benefits that they could pull across from automotive to architectural into that space. more often than not used in its clear form for safety and for security aspects. As you can see on the right-hand side of the screen, iconic project in Paris, France, which is the pyramids at the Louvre Museum as well. Throughout that time, about 20 years ago or so on, there was a continuous innovation in using PVB interlayer and innovating that product so that you could impart additional high-performance capabilities into the interlayer. Things like acoustic above and beyond what you could get from conventional PVB interlayer, imparting solar control properties to potentially be used in conjunction with coated glass to achieve perhaps a lower solar heat gain coefficient. Additional UV benefits for those types of projects where a high UV blocking was potentially needed, museums, libraries, things of that nature. As well as from a structural perspective, so imparting some structural capability into the PVB interlayer to allow it to take some of that, as well as potentially lightweighting of glass. As you can see in the insight, excuse me, the inset image, that's of the Academy of Motion Picture Museum in Los Angeles, California. It was just completed very recently as well, utilizing SafeFlex structural. And then with that, all the colors that can be achieved by utilizing PVB interlayer, specifically the SafeFlex brand of interlayer. So within that, a very simple but a very powerful system that allows you to create up to 69,000 different color combinations, whether it's transparent or translucent within that spectrum. But I guess the key thing among all of these things is that you have a number of different high-performance benefits, but because they're all similar chemistries, you can combine those. It's not all or nothing. It's not one or the other. You have the potential to combine different high-performance benefits in between those two pieces of glass. So with that, let's move on to some the emerging drivers that we see out in the marketplace, specifically as we talk about innovations in bird protection in the marketplace. Bird collisions, a huge issue. I mean, we've seen glass has been used in architecture for hundreds of years, and as we've seen more and more use of glass in architecture, we've seen some amazing, amazing designs come out of that as well. But within that, you know, glass is more or less visible to humans, but with regard to birds, it can become an invisible and even a deadly barrier. So with that, whether it's vegetation behind like conservatories or atriums, things of that nature, reflections of the vegetation on the building itself, whether it be trees or shrubs, bushes, things like that, or the transparency of the building and birds being to see through it, or transparency of sky. Billions of birds are killed annually across the world. In the United States alone, over 1 billion birds are killed annually. In Canada, up to 42 million birds are killed annually. A lot of that as they migrate along continental flyways. So it's a big issue and continues to be a large issue. But I mean, there have been a lot of things happening out there to look at that and see how that potential issue can be solved. And again, protecting biodiversity with bird protection as a part has become mainstay in recent years. There are a lot of things happening with regard to government bodies, agencies, environmental consultants, you know, trying to look at this issue and try to make it better. You know, organizations like the American Bird Conservancy, collabs in Europe, Lee, which actually has a credit now for bird protection, and as we go into Canada, the CSA and Toronto Green Standard. Increase in local law and codes and city building permits. In Germany, a number of different cities, Frankfurt, Berlin, Stuttgart, where you actually have to have a bird protection plan in place before you can pull a permit for a building. North America, we've seen very recently in New York, where the New York Local Law 15 has been enacted, so utilizing threat factor from ABC and a number of different guidelines that have to be in place. Not just there, cities in California, Minnesota, Illinois, into Canada proper, as well as in Toronto. And we've just seen it here through, you know, publications, drawing, you know, creating awareness, growth and awareness, as well as, you know, global events like this where this potential issue is talked about as well. So that's all led to the increase in, you know, bird-friendly or bird protection type solutions. So with that, let's meet a new glazing solution for bird-friendly glazing. And that is SafeLex FlySafe 3D. We have a little video here that we'll show in a second. One thing I want you to kind of check out while you're looking at the video is that there are a couple of things. One is the sequins that are on the glass. That gives you some understanding of why the product is called FlySafe 3D, and from the backside, there's a dark color versus the reflective color on the front. And let me see if I can. So with that, why SafeLex FlySafe 3D? So there's a few things. The biggest issue is saving birds. That's number one. So when we look and we think about talking about that specific area, the solution is actually highly effective. It's been tested in Europe at the Hohenhau-Ringelsdorf flight tunnel there as well. And it had achieved a category or a rating level as highly effective, which is category A, as you can see on the right-hand side of the screen as well. It has also been adopted by American Bird Conservancy and shown as a less than 10 threat factor. The lower number, the better. As you can see from the left, FlySafe 3D actually bodes very well, or a highly effective solution on both of those category, or both of those different rating systems as well. On top of that, and we talked a little bit earlier, that is a lead credit, potential lead credit as well from it, if it's less than a 15 threat factor on the American Bird Conservancy rating system as well. So, highly effective solution. Category A, the highest level that can be achieved, and a less than 10 on the threat factor for American Bird Conservancy. So highly effective. With that, though, there are some other things that come along with that. Normally, to have a highly effective solution, you normally have to have more coverage on the glass. With FlySafe 3D, you're actually achieving a highly effective solution with a coverage of less than 1%. So we talk about high visible light transmission and also not obscuring the view from the inside. It's able to achieve and be highly effective with very, very low coverage. Let's take a look at just how it looks on the glass from the perspective, from an exterior perspective and from an interior perspective as well. Some other important attributes to go along with it as well. Durability. So there's no deterioration of the sequins from the exterior part of the glass because it's encapsulated, as you can see from the right-hand side, between two pieces of PVB interlayer. It's an in-glass solution, so it's not exposed to the elements, contaminants, pollution, or contact cleaning, which you would normally find on a solution that's exposed to the elements. With that also, it provides a level of design freedom. So it's compatible with selective coatings. It's also compatible with selective SafeLex products as well in conjunction with it that could be combined. And the third thing, as we see another trend in the industry of larger and larger panels, it's also available in large panel set up to 3.2 meter wide. All of that, again, by being a highly effective solution. Comfort and protection, I mean, it does meet the safety and security norms. It is PVB interlayer within laminated glass. It meets impact and shower retention. It allows for additional design, comfort, as well as the security that you find in safety from laminated glass. And it acts like conventional laminated SafeLex product. The offering that's available, it's in clear color at 9 millimeter by 90 millimeter grid pattern to start, at a thickness of 30 gauge or 0.76, would be combined with another layer for use with heat strengthened or fully tempered glass, and again, up to 3.2 meter format. Applications, you name it, everything from facades, link bridges, glass fins, balustrade, just a number of different areas where when you need a highly effective solution, has a very low coverage and very high durability, can be utilized in a number of different applications. So how is it different? Take a look for yourselves. So we have some different offerings there. If you're looking at it from the outside in, black dots at about 25% coverage, FlySafe 3D at less than 1%, and vertical stripes at about 12% coverage to meet the effectiveness level. I'll leave it to you to judge which one you would potentially prefer from the outside. As well as if we look at it from the inside, again, the black dots on the left, 25% coverage, 1% coverage of FlySafe 3D, and then vertical stripes, which are about 12% coverage. So what you would see from the inside looking out, I guess the other thing that I would comment there too is it's also about what design is transmitted into the space. So if you actually look at the lower part there, you can see there are designs and how they're transmitted into the interior of the space as well from a design perspective. So with that, we actually have a booth outside. We have samples there if there's interest in taking a look at that, and appreciate your time today. Places you can find us as well, I apologize. Places you can find us online at safelex.com/flysafe, a number of pieces of information, myself or my colleague, or simply at SafeLex, contact us. Thanks so much, appreciate it.
Thanks so much, Michael. Fantastic to have another new product on the market that will help us deliver on that regenerative architecture we need to do to kind of help our planet. So we're going to break into a coffee break, and hopefully you get a chance to have some discussions with some of the presenters. We're going to be back in 20 minutes, so that puts us at 3:40.
Hello. We'll start the last session in a minute. Can I request all of you to please be seated? We'll start the last session in 30 seconds. Can I request all of you to please be seated? Thank you. Have you turned it on? Yeah.
There we go. Hello. Okay. Hey, everybody. We're going to get started again. This is for session 4, getting down to the end of it. But I think this one is going to be a really fantastic one. I've been looking forward to this. So we have Evan Lavelle, Associate Principal at Front, and John Douglas, who's a Pre-Construction Director at Alutech. Welcome.
Yes. Cool. All right, everybody can hear me? Sounds good. Cool, so I am Evan Lavelle. I run the Front London office. This is
John Douglas from Alutech in Qatar.
And we're going to talk about this building, the realization of the Lusail Plaza Towers by Foster Partners in Doha. Do a little bit of introduction, and then get into like how to make a crazy big cold bent facade.
Yeah, so I'm the pre-construction director for Alutech based in Qatar. We have a global presence around the world now, in Europe, Australia, and at the start of next year we'll also be present in Canada. So we're a company that's been in existence for 27 years. We're a facade contractor who deal with some of the most complex projects around today. So you can see the kind of gradual progress of the company. This is just kind of show that we haven't just done this enormous mega project without a lot of experience built up over many years. We started to get into very large projects in 2008, 2009, doing 83,000 square meters of unitized curtain wall on the Twin Palm Towers in Doha, and at the same time doing the Kempinski residence in Doha, which is 295 meters tall. We also did our very first cold bent project, which is an iconic twisted tower, which is down at Hamad Port in Doha. It's by PLP Architects from London. And our first international, or major international project was the cold bent glazed roof on Tottenham Hotspurs in London. Then we got into the really big stuff for the World Cup. So we've been very busy in Qatar for the last few years. So we did the Lusail Stadium, which is the World Cup final stadium for the FIFA World Cup this year. It's Foster and Partners design stadium with about 62,000 square meters of aluminium vessel facade, and then another about 20-odd thousand square meters of internal facades and ground level facades. We also did the container stadium in Doha, which is I think quite a famous stadium, which is built out of a steel structure with all the internal spaces made up out of actual shipping containers. It's designed to be fully demountable. The project that we're going to talk about mostly today is Lusail Plaza, which is a mega project with a time scale from award of project to completion of 2 years, 3 months. And it's 2 70-story towers, super tall at 306 meters, and 2 50-story towers, which are 224 meters tall. So one of the first projects that I was involved in Qatar is the Hamad Port Control Tower. It's a 6,000 square meters of complex cold bent unitized panels with a honeycomb solar shading on the outside. The scale of out of plane on this project was 176 millimeters. The units are approximately 5 meters by 1.2 meters. Again, this is Tottenham Hotspur in London. So again, mega units on this project. So some of the units are up to 4 meters by 14 meters. Every single unit is different. The structure of each unit is a pre-cambered steel frame with a Ryco system on top, and then SGP laminated glazing, basically slightly cold bent into the pre-cambered shape. Very beautiful project. And then we have Lusail Stadium, which, as I said, is 62,000 square meters. Everything is individual and bespoke on this project. All new dies. I think you can see the quality, and everybody's going to actually enjoy this, hopefully, in a few months in the World Cup. There you go. You can see the kind of complexity in the different shapes. It's made out of triangulated mega panels, so each unit is triangular. The mega panel itself is approximately 14 meters by 11 meters, broken down into 4 smaller panels, which are about 7 meters by 5.5 meters. And I'll throw over to Evan.
Cool. So I'm with Front. I don't know if anybody knows who we are. Some people do, some don't. We're international facade consultants. We started in New York, have since grown. We have offices in Asia, Europe, and several places in America. We've had the great fortune of working on some really cool, complex projects over the years, big towers, complex glass things, again, super broadly international, which has been really great. Variety of architects, scales, materials. It's been a really interesting kind of experience. In Canada, we actually have a few projects, the West Block rehabilitation at the Ottawa environment, the Brookfield Place in Calgary, the Père Lassonde Pavilion at the Musée des Beaux-Arts in Montreal. So a couple of projects here as well. We're going to specifically talk today about kind of integrated design and information documentation for design, manufacturing, and assembly, which has been kind of like a lot of my interest over the last 15 years of sort of designing kind of facade systems and kind of documentation and just sort of general model making to kind of facilitate the production and sort of delivery of facades. And a little history of why I'm here with the contractor kind of talking about this is we've done a lot of work in this realm over the last 15 years, starting with HL23 in New York, where we did a procurement assistance on behalf of the owner, did all system design and helped deliver the building. Barclays Center, we were under the facade contractor, sort of delivering the sort of facade information and BIM model. Kukcha Gallery in Seoul is a bespoke chain metal mesh of like 500,000 rings, all hand woven together, which we did a lot of complex modeling. And the project never got realized. Our design build team with Work AC for the African Union headquarters in Libreville in Gabon. Unfortunately, it was a victim of the previous recession. But over the years, we've kind of tried every modeling methodology, frameworks, software platforms to really work on how to deliver information, how to document information, and how to think about how to get the right stuff to the right people. So we've kind of gone through all these different strategies, trying to understand, like, okay, what's the best way to do this, right? And then that kind of led to the development of 2 kind of ideas for us. One is this thing we call building information generation, which is a kind of internal framework for delivering building modeling and fabrication information, as well as kind of our own kind of custom software we develop. It's also freely available if anybody wants it. It's kind of a BIMifying Rhino, sort of attribute management, things like that. It led us to a second kind of class of projects, a bigger scale, more complexity. The Morpheus, we worked underneath the facade contractor to deliver the exoskeleton cladding. BAM South, we were consultants and then novated over to the facade contractor. We did the Space Needle renovation recently as well as the UC Davis, the Shrem-Yanedi Museum with soil and a design build team, where we helped deliver the canopy facade. Kind of quickly to give you a sense of like how this kind of works with the Morpheus. Basically, we're responsible for the whole design and final design and information and fabrication package, from system kind of panelization, final engineering, BIM modeling, fabrication documentation, assembly, kind of survey and all that kind of stuff, and how to put it together. Kind of, you start with a model, you build one panel, and you build a ton of panels. And at the time, this is a big project for us. It was like, 1.7 million unique parts. Blue Sail's a lot bigger. We'll get to it in a second. But it was kind of nice because it worked out really, really well. Come on, you kind of get a sense of the complexity This is the naked kind of primary structure before the cladding on. You get a sense of the scale of the cladding, the sort of complexities it fits on. In the end, this turned out really well. This is not a rendering. Actually looks, I think, better than the rendering itself. And that led us to the sort of next class of projects where we have Lucille Plaza Towers on the left, and then the Henderson in Hong Kong, which is a new development by Zaha Hadid and Henderson Land. And I'm going to talk about Lucille because it's kind of been my baby the last 3 years. And for us, it's been interesting. So we were originally the facade consultants under Foster & Partners. And then the developer kind of novated us over to the design build teams under Hyundai and B6. B6 developing the 2 shorter towers. Hyundai is developing, or the contractor of the 2 taller towers. And then we worked under Alutech as a sort of consultants, fabrication information, BIM modeling, to help them develop the cold bed facade. It's a little bit of a project team itself. So we'll talk a little bit about in this presentation is how do you go from this sort of conceptual idea, kind of your computer modeling and all sort of documentation into what is the real product at the end of the day. And we feel the fidelity between all 3 is actually pretty good. Still under construction. We should be finished actually in a few months.
2 to 3 months.
Exactly, 2 to 3 months. He said it, not I. Here we go. So we get a sense of scale. It's absolutely massive. It's 2 51-story towers, including the roof, 2 71 towers, including the roof. So it's, what, 244 stories worth of stuff?
Yeah.
Yeah, it's a lot. 411,000 square meters of cladding area. There's 23,000 unitized panels. We've got 85,000 square meters of cold bent glazing. I mean, I work at Metric. That's, what, 950,000 square feet of cold bent glazing. A maximum out of plane for the glass is roughly half a meter, 445 millimeters. We've got 271 kilometers worth of curtain wall framing, 8.5 million unique fabricated parts. From a data standpoint, from a modeling, we've got 1.2 terabytes in the model, another 2 terabytes of fabrication data that gets pushed out into the factory. And so it's just sort of like what we go to in this process is like, how do we enclose a building that's of sort of this shape? How do we manage the scale from designing at first principles, fabrication documentation output, assembly and information, because it has to flow through the factory at a very quick pace. More of kind of about reducing the scope of the supply chain, kind of consolidating in-house.
This project is every factory's dream.
And then, like embracing complexity and just like designing for complexity and not trying to optimize, because again, computers kind of rule the world. And then basically, almost near paperless design where we're doing everything direct to CNC, straight from the model, which has been an interesting process. So the question is, why cold bending? Here's some panels recently in the factory. And you can kind of look here. You've got kind of, this is the massing of the tower, kind of got these morphing shapes where basically they're the same shape on the top of all 4 towers, but they're kind of different size, a little bit squished, so they're not actually the same. And then in between the 2 towers, there's subtle differences that don't make them quite the same. And then, so if you look at kind of between a flat panel and a cold bent panel, you can kind of see a lot of things that are happening. One, flat panel, you've got, it's kind of you think of it as the easy solution, like, oh, flat panel, it's complex, let's just do that. But it actually introduces a lot of things where you've got a lot of variability between the panel itself. You got little bits of aluminum, little fiddly bits to deal with. You get waterproofing issues, you got thermal issues, all sorts of stuff, installation issues. It actually becomes a bit of a nightmare. So kind of working with everybody in the project team, we're like, hey, let's embrace cold bending. I think we can do this. So that's kind of like what I went through. From a energy performance, it's a no-brainer. So if you've got a kind of perfectly flush facade, you can kind of very well control and very understand all of your kind of thermal issues, your condensation issues, your waterproofing issues, all that kind of stuff. Acoustic flanking, all of that's really, really good. The moment you go to the popping scheme where you have to deal with this sort of out of planeness, especially like up to a half meter out of plane, you end up with a bare minimum 9% drop in the thermal performance up to 32%. And when you look at it at the worst case condition. And if you kind of multiply it over the building, that's really bad. So with a cold bending solution, as you kind of run the full building energy analysis, we end up about 31% under the sort of local environmental targets with GSAS is running that kind of in the building. So from an energy performance, it's a fantastic solution. So it's like, okay, this is a no-brainer. So how to cold bend at scale? This is the really big question. And so I'm going to talk about the first three things. John's going to talk about the fourth thing here. And the big things to talk about are your computational frameworks. Like, you know, you have a lot of stuff to cover in a short amount of time. So how do you design all your computational processes? Designing the frame, we'll talk about that. Talk about design and kind of engineering of the glass. Basically, how to mass customize the glass at a very big scale. And then here, he's going to talk about kind of putting it all on one roof, organizing, and kind of taking all this information and running it through the factory. Computational frameworks. So there we go. I'll talk a little bit about graphs. So anybody's familiar with sort of modern sort of computational design? Most sort of platforms now run on basically a graph. So you have a directed acyclic graph, Grasshopper, Dynamo, all these kind of things, the stuff from CATIA. They're sort of graph-based things that kind of move information through, and they sort of reflect either points of states, or they reflect little bits of models, or things like this. So what we've done over the years is sort of thought of the entire model, the entire design process as a graph itself. So each one of these nodes on the graph represents a model, represents an output, represents a state. And so you can actually build an entire database that's composed of tiny, tiny small elements that make these sort of massive models very easy to work with. You can query them, you can combine them, you can do whatever you need to do with them. You can revert to them, do all this kind of stuff. So it makes the sort of, gives it a lot of flexibility to the process. What that means in reality is that, you know, you have lots of different software that develops these buildings. Try to be software agnostic. You've got Revit, you've got Rhino, you've got Excel, you've got Project, you've got AutoCAD, you've got FEA software. They all have to work together. You use this kind of graph to kind of move information through. So in reality, kind of what that looks at is you have all these sort of moments. And so this is an early wireframe model, and it's like kind of early in the graph. And the wireframe kind of represents a lot of stuff, the information you have. Kind of, you know, if you look at a wire, you kind of know what mullion it belongs to, you know how to cut it in the end, you know kind of what panel it belongs to, you know who made it and things like that. So it's a state in the model. It's relatively lightweight. I mean, but it represents every single part in the building. Kind of moving further down the graph, another one could be, say, the wind load analysis. We take the 2D information for the wind load model, map it onto the building, and then another portion of the graph is developing a kind of a spreadsheet someone's like the contractors use to determine and load conditions and things like that. Let's see here. Next in the graph is, we did a lot of FEA. And so here we did a full building FEA very early on in the process, determine all the slab reactions. So we're designing the slab anchors. And we can, you know, early on develop like the boundary conditions, produce a table. So whoever needs the information, whatever format they need to see it, sort of the model will deliver in these little small increments.
Yeah, being able to get this kind of data in such a readable format allows us to make decisions really quickly. That kind of helps.
Yeah, because I mean, engineer wants to see the graph, I mean, the spreadsheet. We want to see the boundary conditions, and then someone wants to prove that it was done. So that's kind of what it is. And then the same model, you know, it's the same model. You can then add a little bit more detail further down the graph, produce all the reports you need for all the engineering analysis, justification, things like that. Other bits of the graph are here. We're looking at kind of, now we develop a full parametric model of the building. We're comparing it to the sort of design intent of the architect in this case. And we're using this to determine, you know, the distribution of panels, the outplanarity and things like that, which, you know, gets wrapped into the cost modeling and things like that. Another view in the graph is just a point where we're determining the glass makeup. And so looking at different thresholds of out of planeness to do the cold bending. And so basically at 125 millimeter threshold, use one type of glass, and then above that, you have to use a more expensive glass. 150, you have less than more expensive glass, and 180, you have the least amount of the expensive glass. But another thing about it is the expensive glass is not only as expensive, the time it takes to make it.
Takes a long time to actually do it.
And,
yeah,
you know, we couldn't actually produce the building in time with this glass.
Yeah.
Another bit in the graph is when we're kind of ordering all of the extrusions, and we were working with the system supplier about different ways to measure the extrusions, the angle between them to find, and there's very subtle differences, but it ends up, you know, working at a very big scale. You could order, you know, 250 kilometers worth of the wrong extrusion, which would be a very big mistake. Other parts of the graph, kind of looking at panel sizing and things like that. Another key thing here is that we were able to go really far ahead of everybody. We completely designed the system, and and then took that system information, all the constraints, and turned it back into the slab edges of the building. So we actually dictated the building form as a response to the facade, such that when we go to install later, this building's popped into place. Producing Revit models to check and design intent, things like that. You know, checking BOQs to do all the mullion ordering, all of it just to figure out how much of the transoms to buy and things like that. The framing itself, I'll go through this. So there's a traditional way to cold bend is you kind of build a flat panel, you push one corner, then what happens is the transoms kind of rotate and the mullions rotate. However, architecturally that was not viable because we had designed a perfectly flush transom with the floor finish. So we knew we had to find a different way to sort of build the frame. Another problem with the traditional cold bending methodology is that you get this twist in the mullions. However, because of the peculiarities of that process, it means that the neighboring mullions would not be parallel to each other, which means makes insulation difficult, brings in weatherproofing issues. So we're like, okay, we can't do this process. Another problem is, you can see here, this is kind of what's happening with the twisting transom, but the key thing is that the glazing type is going all the way around the corner. And while it's ideal from a glazing perspective, it's not ideal from an architectural perspective. More of a kind of simpler way to do it means that you kind of line the transom and the mullion together, but the glazing tape is non-continuous. So then we had to do very subtle rationalization of the overall building to make sure the glazing tape is consistently around the edge of the transom and the mullion, which then allows all the warranties to kind of flow through from the glazing tape manufacturer. To kind of do that, so we have to do a complex, complex miter of all the transoms such that the panel itself will form into 3D to make all this kind of work. Kind of go through, I'll skip going into the particulars of this, but 3 different ways of kind of computationally understanding how these work. We chose these middle counter twist method. It means we build all the panel in 3D, which is interesting from a fabrication standpoint. We thought it was going to be difficult. It actually turned out to be
it's actually very efficient,
a really good way to do it. The key thing about this, though, is there's no residual no residual stress in the structural silicone with the glass in the frame, because you're building the whole panel in a 3-dimensional shape. You can kind of see here, this is our first prototype, like 2 years ago. Very subtly, you can see the mullion kind of twisting into shape around the complex miter on the transom. It was sort of like proof in the pudding that it actually worked.
Exactly. Yeah.
Which is good. That's that. I mean, the cold bending process is this. You kind of make the panel into 3 dimensions. You put the flat glass on. The flat glass kind of forms the shape. You do your structural glazing in a 3-dimensional shape. You let it cure in a 3-dimensional shape. And then you can let it go back into 2D or a flat shape for shipping if you want, or you can leave it in a 3D shape. It really depends on, you know, your logistics.
It's just transportation, yeah.
And that results in a kind of 3-dimensional frame like that. The glass, let's see here, okay. We've got plenty of time. So you can hear we're putting a kind of a formed piece of glass over a panel, and without much effort, it kind of falls into place. And so that allows us to go into the sort of glazing room with with very little bit of pressure on that glass. So the next thing is, like, how do you go from your kind of conceptual model wireframe to a real surface to an unrolled sheet for the CNC processing in the sort of machine? And this is kind of talk about this first part. So computationally, your CAD software knows nothing about material properties. And so I won't get into the peculiarities of NURB surfaces, but you know, the panel itself is defined by 4 edges, and it mathematically just sort of equation that just determines what the surface is in between. But once you start to apply material properties, you can see in below, that's actually not the shape of the glass. And if you start to unroll that shape, you get a very, very different shape, and it won't fit in your frame. So we needed to figure out a way to predict the unrolled shape so we could do, you know, cut the glass and put it back in the 3D shape. You can kind of see here, this is a sort of a model of the panel. It's the same panel below. You can kind of see the shape. You can kind of see the counterflexure and all that kind of stuff that is coming on the panel. So what we do is we run it through a shape function. Basically, we pick up a few pieces of parameters on each piece of glass. We run it through a series of equations through a poor man's machine learning to determine, kind of predetermine some panel shapes and unroll it like that. So we run it through approximately 3,500 simulations to kind of train the model of how to kind of automatically unroll all these sheets of glass. And you kind of see here, this is one panel, 4 panels. These are all different panels, by the way. You can kind of see how the stresses kind of resolve. But we just basically do it for every panel on the project. Yeah, it's a lot of panels. It's a lot of panels. Yeah, okay. And so then we go from the surface to the unrolled shape. Basically reverse that process in the same FEA software and basically push the panel into its flat form. And you do that again a lot, reverse the process. But at the end of the day, you have a DXF file, an automatically generated kind of 2D sheet, feed the DXF into the CNC machine, and then the guy checks it with the sheet. All this kind of engineering, just have a really dumb deliverable, but I think it's important. Then you have lots of glass. Now to John.
Okay. Yeah, so I think one of the basis of this project as well was that it had to be as sustainable as possible. It couldn't be a zero carbon. It was way too early for anything like that. But there was a kind of a push to use as local a supply chain as possible. So actually we're lucky in Qatar, we have a huge smelting plant called Qatalum. So in relation to the aluminium profiles for the project, I mean from the smelting plant all the way to the actual project site is 20 kilometers. So we had this very, the billet comes from Qatalum, goes to an extrusion plant, which we're a part owner of, Calex, through the finishing, the coating at our own plant. The glass processing was also at our own plant. The cladding is at our own plant. The assembly is at our own plant. And then the site is 20 minutes away. Obviously, if you're going to approach a mega project like this with this level of complexity, and you approach it in a parametric way where everything is exported in files to go directly to machines, you have to have the machinery. So this project was a little bit special in the fact that all the cladding on the outside is anodized, but the cladding sheets are as big as you can actually purchase. So in depth, they're 2.6 meters. And what we found was there was no anodizer in the world that could anodize a sheet that was 2.6 meters deep. So we had to build the world's biggest anodizing plant. So we built a 3.1 meter deep anodizing plant specifically for the project. We also took in a very large format, 6 meter by 3 meter possible IGU line from Lysec with the super spacer, which is a flexible spacer. And obviously we have a lot of CNC machines, etc. So you have to have a lot of machine power to deliver this in 2 years, 3 months, which is what we've achieved. Yeah. So in order to reduce material wastage, part of what we did was we bought bigger machines. So we bought as big as we could get, and if we couldn't get them, we invented them. So these are AXYZ routers. Actually, they're from Canada, and they are 14.4 meters by 3.6 meters wide. 3 of those working 24 hours a day for the project. This is the exceptionally deep anodizing vat. These are the smaller triangles. You'll see in a second the actual the large-scale triangles, I think, start to come out now. Nope, that's the smaller ones again. Maybe they're on this video.
Yeah,
at some point, I think they're coming.
This one. There.
Nope.
There it is.
Yes,
yeah.
There we go. Yeah, so it's a really massive panels. And then you get into this final assembly plant. So this is the assembly plant for the vision panels, so where all the cold bending is done. And it's just this constant dance, yeah. In order to deliver this project, this runs 24 hours a day. There's about 11 factories involved in our own company in this to deliver these 23,500, 24,000 unitized panels. And it's just a continuous process all the way through. And then, yes, every single panel is completely different. Every single part of every single panel is completely different. So it's managing this complexity at a very, very large scale. And I think that's really the huge achievement of this job, is that we genuinely figured out between ourselves and Front how to deliver that complexity didn't matter, even at scale. So the process between the parametric design that we did and how we managed it in the factory and the process all the way through was very effective. It's complicated, but effective. This is the install at site. So what you see on the left-hand side is the last panel being installed on a floor. So it's the spike panel. As I said, everything is cold bent. Every panel is out of plane. So every panel has fitted first time. We haven't had to remake anything on site in order to fit. And that's kind of, I mean, a lot of the credit has to go to Evan for this and to our guys on the factory floor for maintaining these tolerances.
I mean, we're installing 206 panels a day.
207 panels a day is what we were installing, which is quite an incredible achievement, really. I mean, scale-wise, this project is, I think, 2.6 times the square meterage of the Burj Khalifa, just to kind of get a feel for it. It's a little bit insane. You can see these panels, they're really massive. So they're 1 meter, the fin is 1 meter out from the actual facade. Tip to tip, it's 7.3 meter panel. It overhangs into the unit below by about 3 meters, which is a nightmare for the installers, I have to say, but that's life. Yeah, it's just an enormous scale. I mean, you can even see the quality. This is anodized, yeah? I mean, the quality of the anodizing from our guys in our plant has been spectacular on the job. Just mountains and mountains of complexity on this project. But yeah, these are a few months ago. The smaller 2 towers now are just about topped out, and 2 larger towers would probably have been topped out, but we're about 60% winded off on this project for the last 8 months. It's unbelievable how unusual the weather has been throughout this job. And we're just going to finish off with an install of one of the complex, very large panels. They have to be lifted from the ground due to the overhang. You can't do from the actual slabs. I think the guys had this, for the opaque panels, these panels down to about 12 minutes on average for install, which is pretty good. So that's what it takes from our point of view to deliver
Very brief version of what it takes.
Yeah, absolutely. Yeah. Absolutely.
Cool.
Okay.
That's it.
Perfect.
Check. Hey, thank you so much for that. That's kind of like an unveiling of the level of complexity that goes into a tower of that type. And just a little over 2 years. That's crazy. Wow. It kind of goes to show like the kind of where we are now within prefabrication and design for assembly. It's manufacturing and assembly. Just there's when you see companies like Katera kind of go under, in terms of that prefabrication, the amount of intelligence it takes to actually do the work that you're doing. Yeah. Yeah, that's fantastic. Thanks so much. Okay, up next we have Brian White, Technical Section Manager for Insulating Glass in the Americas for H.B. Fuller. I think he's just getting wired up here right now.
Okay, can you guys hear me okay? All right, there's this. Got the little... All right. Well, hello. Hello. My name is Brian White, Technical Manager for North American Glass for H.B. Fuller. And H.B. Fuller, today we're going to talk a little bit about Cody Space 4SG reactive TPS. I want to talk a little bit about how it's the key to energy efficient facades and also high performance facade design. But first, just a little bit about Fuller. So you guys might be asking yourselves, why is a adhesive and sealant manufacturer at the Zach World of Facades? And it's because we really want to start to promote and discuss how our spacer technology can help enable high-performance facades. And we also want to drill down a little bit. So we talk a lot here about the the facade, the entire building design, and we really want to drill down into that insulating glass and help you understand how IG, or the important role that IG plays in the building facade. But H.B. Fuller Cumberland, we're a global market leader of adhesive and sealants for IG application. We've been at this since the late 60s, kind of since the birth of IG almost. We've been focused on continuous development of technical products and application solutions. We provide all sorts of high-performance sealant systems. We are a provider of IG sealants, a provider of warm edge spacer systems that we'll discuss a little bit today. Also structural glazing solutions, different window bonding technologies, and also wet lamination products. So a little bit about what we see as kind of the glass facade market trends. We know that energy efficient buildings are being, more and more energy efficient buildings are being demanded of us. We all are aware of that, and we saw a lot of discussion about that just today. Obviously, energy standards continue to tighten, things like the European Directive in 2010, and also NFRC driving higher and higher standards like Energy Star 7 and beyond. We also see, as we saw in the talk just previous to me, that people are looking for a lot of innovative shapes and designs for their facades. So curves, bent glass, polygons. We're asking a lot of the IGU systems here, and so we like to talk a little bit about how we can help enable all those different innovative shapes. Also the innovative designs, large glass panels, jumbo units, and also functional facades. So incorporating solar, LED, different type of chromogenic or solargenic coatings, things like that. So we're seeing a lot more demand on the IG unit in the facade. So just to kind of back this up a little bit, I want to give a short introduction to IG. Now, a lot of you might, it's interesting because we look at, or I've seen today, a lot of different FEA models, designs, things like that, and the IG is kind of treated as a monolithic panel, which is more or less the case. But it's actually a living, breathing design or piece of the building all of its own. So we have really four main parts to IG. We've got the glass, so that's going to provide your vision space, your substrate for coatings. We've got the spacer, which is going to hold those two glass lights apart, or 3 or 4, depending on the IG unit. That's going to create that insulating cavity, and also the spacer is going to contain the desiccant to keep the interior of the IG dry. We're also usually going to have a noble gas in that unit, so something like argon or krypton, even xenon in really high performance units. That's going to improve the insulating value of the cavity. And then we also have a primary and a secondary sealant. These sealants need to do a couple of things. They need to adhere the IG components together. They need to seal that cavity of the IG for the life of the unit. And when we say seal it, it also needs to protect against penetrating humidity, or we need to keep moisture out, because once you get moisture in an IG, it no longer is insulating. We need to keep that gas in so that we keep the insulating value over the course of the lifetime. And then also the sealants have to absorb and diffuse mechanical stress that IG sees over its lifetime. So when we look again at some of these FEA models and see IGs being bent and shaped and things like that, of course that's going to put stress on an IG. But things like the daily temperature swings, weather systems, high pressure, low pressure, all this kind of stuff. If you think of the unit or the IG unit as a sealed cavity, what happens to a sealed cavity when you heat it up? The gas inside it expands. So that IG unit on a day-to-day basis is breathing and moving and pumping, trying to almost force its gas out and let moisture in. So the sealant has a really important job to do for the 20, 30 plus years that we expect an IG to be in the building. So to introduce thermoplastic spacer a little bit, or the kind of the topic of the discussion, what we look at for a traditional IG is there's a couple different main components. So we talked about the glass and all that stuff, but for the edge seal, we've got the primary seal, which we see in the little green area down here. I don't know if I got my pointer, yeah. So we got a little primary seal in the green area. We've got the metal spacer and the desiccant kind of in the middle there. And then we've got the secondary sealant kind of holding that all together. So what TPS does, or what thermoplastic spacer does, it replaces that primary seal, the metal spacer, and the desiccant all in one material that's extruded directly onto the glass. And to take that a step further, we want to introduce CuddySpace 4SG, which is, to us, the state-of-the-art TPS. So this is a reactive material. So for those of you that maybe have some chemistry background, this stuff actually cross-links. So it'll create a chemical bond both to the glass and to the silicone if you're using silicone as a secondary sealant. It'll internally cross-link. This gives you a higher service temperature. We're seeing a lot more and more demand of temperature extremes on IG. So this gives you a higher temperature service, or higher service life, higher service temperature. Gives you resistance to incompatible glazing materials, which is a topic in and of itself, and gives you also a permanently elastic, fixed, and cohesive edge seal. So this is, again, bonded to all the different components and really creates a nice, positive, permanent seal. The material's been approved in structural glazing applications. It's been active in the market since 2009 and has really been extensively tested and certified to all sorts of different alphabet soups that you see at the bottom there, anywhere from SACAL, FGIA, IGCC, ASTM, et cetera, et cetera. So why are we talking about this spacer? Well, the biggest reason I want to talk about the spacer, as I mentioned earlier, we want to, again, allow people to understand how spacer technology can help enable more energy-efficient facades. We want to think about energy efficiency for the long term. So it does no good to make an IG unit, fill it full of gas, stick it on the side of a building, and then that gas just works its way out, the moisture gets in. All of a sudden, all that insulating value that you put into the calculation of the total building performance no longer really means anything. We want to make sure that we have this energy efficiency over a long term. So we all know energy efficient IGUs are going to reduce CO2 emissions over time because we use less heating, less cooling load, create that interior space that's much more comfortable and over time decrease energy costs and the carbon footprint. The real big efficiency drivers of this, one is going to be the low E coating, and one would argue that's probably the major driver of efficiency in an IG unit. The insulating gas fill is going to drive another about quarter of that performance. And then the edge system itself, as we're aware, also delivers some energy performance in terms of its ability to thermally break heat movement across the IG. But really, at the end of the day, it's that ability of the edge system to both retain the gas and prevent low E damage that's going to drive the long-term efficiency of an IG unit, and thus the facade over time. So we might say, how does the spacer help enable this? Well, insulating glass, it endures a lot of different stressors, right? So I talked a little bit about it earlier, but the temperature extremes, the humidity extremes, the wind loads, pressure differentials, all this puts stress on an IG unit. So the sealant's going to be stressed at temperature, it's going to be moving, it's going to have a tensile force, a compressive force. The airspace volume that I mentioned is going to change, the glass is going to deflect, moisture is going to try to work its way in. The edge seal will be under a lot of stress really throughout the entire life of the IG unit. In addition to all that, differential thermal expansion of the lights of glass really comes into play when you have a cold exterior, a hot exterior, and a room temperature interior. The exterior light of glass is going to get larger and smaller and going to expand and contract along with those temperature changes. So that puts a asymmetrical stress on the sealant and on the spacer. So this is what drives it back to the spacer system, and we really talk about the importance of elasticity. So stress can result in strain in an IG unit. From an engineering perspective, stress results in movement, which is the strain. Rigid spacer systems, they often compensate for this strain through glass deflection and primary seal deformation. So we see in our little pictures down here, a compressive force is going to squeeze that primary sealant, typically in a dual seal system that's polyacetylbutylene. And then when the airspace expands, it's going to pull it apart, which can result in seal damage. Thermoplastic spacer can elastically deform and minimize the glass movement. So what we actually end up seeing through a lot of experiments that we've done in the past and a lot of FEA modeling that we've done in the past is that when you use an elastic spacer system or a flexible spacer system or movable spacer system, that it'll actually compress and expand or compress and elongate and actually allow the glass deflection to be minimized because that strain doesn't have to go into the glass. It can go into the spacer as well. So it's a real big benefit to reducing overall movement in the IG. Similarly, we talked about its ability to compensate, for thermal deflection or thermal contraction. So again, we see a temperature drop outside, that outer pane starts to contract. In a rigid spacer system, you've only got a little bit of primary sealant that's making up that barrier. If you contract that pane, you can actually squeeze and move that primary sealant, and in some cases, you'll compress it too far and create a primary sealant failure. For Cuddy Space 4SG, that movement or that spacer can go right along with the glass, and then we'll just go right back out when the temperature change is gone. In addition, we look at, and this is a triple in particular, but we have fewer and longer moisture ingress and gas egress interfaces. So when you look at a conventional IG, these are all interfaces between materials. You've got glass, sealant, sealant, spacer, spacer, sealant, sealant, glass. Whereas here, you've just got glass, then spacer. And on the other side, spacer and glass. So you have fewer avenues for moisture to get in and gas to get out. Now, we've tested this over time. For those of you familiar with European standards, EN 1279-2 is a weather cycling pattern. It's about 3 months worth of accelerated weathering. What we've done in the past is gone and runs IG units made with this spacer through 5 runs of EN 1279. So this would be about a year and a half of testing. And what we find is argon concentration. We find a really good argon retention, so running about 4% loss over those 5 cycles. And then also about only 12% of the moisture capacity of the desiccant is used up over that time. So this unit still has 90% of its moisture capacity left. Excuse me. Okay, another thing we can do with 4SG is really enable a lot of design freedom. So we can do all sorts of planar shapes. We're not limited to boxes and rectangles and triangles and things like that. You can do any kind of shape you like, whether you've got kind of a curved top up here or rounded edges or trapezoids or anything like that. We can do jumbo units very easily. You can imagine for rigid spacer systems, the fabricator has to go and actually hand place that rigid spacer. Now, when you get to a unit that's the size of some of these units we're seeing these days, I mean, it is not easy to do. It is not easy to do with any level of precision. And again, I was really excited hearing about all the cold bent work because this particular spacer system really enables cold bent units. So you can imagine with a rigid spacer, it's really hard to bend a rigid spacer, out of plane. It can cause a lot of damage to the primary seal and you end up with a failed IG unit. Whereas with 4SG, you have this flexible spacer, it just bends right along with the glass and really does a great job making a cold bed unit. Case in point, one of the projects we've been involved with. So this is the Chadstone Shopping Center in Melbourne, Australia. This is the sealant and spacer here. The sealant used here on the spacer was 4SG and then a silicone spacer, or silicone sealant. The IG manufacturer is Show Glass, the facade company is Sila. This was completed in 2017. It's the largest shopping center in the Southern Hemisphere. And this glass roof is 260 meters long, or about 7,000 square meters of bent glass. So all these were bent into place and to create the roof of this beautiful shopping center. There's a couple additional pictures of it too, so you can see just the scale of that bent glass roof, not only from the outside, but then from the inside as well. A couple other projects we've been involved with, so 102 Charlton Street in New York. This is another 4SG building, a little more traditional. With no real bent glass, but again, a project that was just recently completed in 2021. Let's see, another project. So I'd like to see this, and I've heard this project talked about all day today, which is fantastic. CIBC Square. This was also used at 4SG, which the IG manufacturer is Viracon. The architects Adamson Associates and Wilkinson Eyrie. I know the one building I think was completed in 2020, and the other will be in 2023. So we've got 270,000 square meters here for a LEED certified and WELL building standard certified project. The Parnas Tower and LG Science Park in South Korea. So here we've got 25,000 and 98,000 square meters of IG, all put together with 4SG. Another one too that I saw earlier, I think, what was it, the second talk of the day, we talked about the Expo Center in Kazakhstan, in Astana, I think. The actual, so that spherical building in the middle, unfortunately that wasn't 4SG, I wish it was. That was a really cool building. But the 2 expo centers on either side of it were also actually 4SG as well. The Newton building in Munich, Germany. This one, this is the TÜV Süd building. The roof of this is a cold bent insulating glass roof, so you can see the roof over here was enabled using this 4SG spacer. So to kind of wrap this all up, 4SG, it's a reactive thermoplastic spacer system, replaces the conventional spacer bar, desiccant, primary sealant found in rigid systems. It improves the adhesion of glass in the silicone secondary to create that cohesive edge seal, improves chemical resistance to incompatible materials that might be in the glazing cavity or anything like that. Yields really good thermal performance in combination with long-term durability. So it diffuses and mitigates that stress. That elasticity of the system is second to none. You get low U values, that gas retention is second to none, and really at the end of the day, it creates that energy efficient facade that we're all looking for. It's also used in some of the most demanding facade applications worldwide. As you saw, the jumbo units, the shapes, the bent glass, all these are possible using this thermoplastic spacer system. So with that, I thank you very much.
All right, thank you, Brian. Thanks for introducing that new product. It's great to have things that are going to be increasing the durability and longevity of our buildings. So that's great. Next up, we've got our panel discussion, and I'm going to introduce the moderator, Stephen Painter of Gensler. He's a principal at Gensler, and welcome to the stage.
We good? Okay, just give us a few seconds while we set up some chairs. Okay. I don't have any panelists, though. Yeah. It's going to be very boring without panelists, I'm afraid.
Hello. Yep. So we have Stephen as the moderator. We have Enda. We have Anik. We have Jelena, and we have Joshua.
Did you get a mic?
Right.
Okay, we're just missing one mic as well.
One mic?
Yeah. All right. So welcome, everyone, and I hope you've enjoyed the day looking at all the amazing technology and facade systems that have been on display here, and the great speakers as well. As to kind of close out the day, we're going to talk a little bit about technology and what's happening, but really we want to focus on where the market is going, what we're seeing across the different industries and different building types that we're doing in Toronto. And with that in mind, we've assembled a panel from different walks of the architecture, construction, and development life as well. So I'll do the introductions. If you don't mind standing up when you talk about yourself, so that people can see, because I was sat at the back earlier and couldn't see anyone that was sat down. So we'll start with Enda, if you want to introduce yourself. It's a good job we're not talking about technology today here.
Okay. Can you hear me now? No? Yeah. Okay, here we go. Okay. My name is Enda McDonough. I'm a principal with Montgomery Seism Architects.
My name is Anik Teasdale St. Hilaire. I'm a facade engineer with Morrison Hirschfield.
My name is Jelena. I'm with Ellis Don, and more specifically, Ellis Don's Construction Sciences Division.
Hi, I'm Joshua Laux. I'm the Chief Development Officer of Mizrahi Developments.
Thank you very much. So we're going to start with talking a little bit about where the market is going, particularly around sustainability, which is a hot topic with ESG investments and so on at the moment. Enda, you've been working on some new passive house projects with really high performance facades, new systems. Can you tell us a little bit about what you're seeing and how you're actually making that work on the first few projects that are going big scale passive house?
A lot of the challenges that we're seeing is trying to have the GCs and the trades understand that there's nothing different here. It's just about it's almost enacting or building the details that we've been looking for, or building the detail quality that we've been looking for years. So Passive House is in essence a police for the quality. And we're also, through some of our modular projects, we're able to investigate different systems that are available out there that we can panelize or modularize or that integrate well with the modular projects that we're doing. So we're starting to develop, to help the contractors and help the trades understand what we're doing. We develop almost like a Lego manual for building the tricky details. So we'll go step by step through the substrate, the sheeting, the membranes, the overlaps between different products and different materials to get that, to sort of bring the cost down ultimately as the understanding gets developed.
Yeah, to really kind of simplify it and make sure that people know how it's getting put together.
Exactly.
So they're not as scared of it, perhaps, as they have been.
Exactly. They're empowered with the knowledge for how to put the detail together. They see then that it's not dramatically different. They're not spooked by Passive House then. They know they can do it. They know they've done it before without the Passive House tag. And so it becomes sort of a normal process for them.
Yeah. A big part of understanding how the buildings come together and being able to draw those kind of details comes from the design team, people like ourselves being on site and actually going like, oh, someone needs to get their hand in there, someone needs to build that. Anik, you've been doing a lot of that kind of work, but over the last 2 years, almost none of our graduates, none of our new architects have been able to go to site. How are you dealing with that, and how are you going to be able to build that knowledge back up that's, at the moment, a bit of a knowledge gap for a lot of people in the industry?
Yeah, that's so true. So as we all know, the critical control layers in the envelope are hidden behind the cladding, whether it's outside or inside typically, right? So it's really important to get out in the field to understand before all those finishes are in place, understand how those critical control layers are put together, understand the sequencing. And another aspect is beyond the actual opaque wall or even the window system or the roof, the details are particularly important. Understanding how those 3D configurations come together, that has to take place on site. There's limitations to what we do in 2D drawings, and we've seen some fantastic ideas today in terms of 3D modeling to understand how that comes together. But going on site is super critical, and I think it's really the best way for new grads to learn. So if you're new, or if there's people in your firm that are new, they need to get out there. It's really critical.
Yeah, it's interesting seeing some of the previous presentations with the amount of detail in the 3D model. And then when you get to site and you realize it's like covered in crap and construction debris, and you're like, oh, maybe we need to rethink it a little bit. Yelena, you're really on the side of the contractor and making sure the stuff gets executed, telling the architects that they don't know what they're talking about, and making sure the trades get stuff built. While your microphone is still muted, I can say anything about you. So. What are you seeing as the gaps, in making sure the design team know how to execute something, making sure the trades really understand the design intent and can pull it off as well?
That's a really great question, and I think to answer it, I do want to touch on Passive House, where the actual execution on site is everything. It's with something we actually get tested on at the very end with that air tightness test. So one of the first things that came to mind is that in a Passive House type of project, we actually include a separate section in our contracts with our trades, whether they're envelope or other, that they have a contractual obligation to meet all the various Passive House requirements. And this adds an added layer of engagement and accountability, so they know what they have to expect. With that, it was mentioned earlier with these transitions and details, it goes way beyond 2D. So there's often a big gap in execution when you see a 2D drawing and have to figure out how to build it on site. So on my end, on the GCN, our responsibility is to really figure that out and to take the contract documents and say, okay, who's doing what, where, when, And we do this through various ways, and those are coordination meetings, engaging our designers and envelope consultants, facade experts in discussing these details, and then sometimes finding that we actually have some limitations on site, either with access or something with schedule that has to be adjusted to make sure everything comes together in the right order at the right time. And then, of course, there will be periodic field testing that will actually verify that we're hitting these metrics, whether it be an air tightness or thermal. So altogether, it's about setting expectations very early and continuing them throughout through the consistent messaging and meetings through envelope coordination, and then ultimately at the very end verifying it, whether it be a passive house air tightness test or some other methods that we're sometimes required to do.
So we've seen other companies today, and I know Elliston are doing it, having people act as that bridge between the design team to ensure the design quality is maintained, and so is the execution, make sure the trades are actually doing what the design intent was. How difficult is that? Are you spending a lot of time on site telling people what to do, trying to resolve issues, calling the architects up, or is that gap narrowing, or did it get worse during COVID even?
Oh, that's a good way to put it, like how COVID affected it. There's pros and cons. I think what COVID forced us to do is actually sit on our computers and look at drawings on the screen. And it's not something we used to do in general contracting or in construction. We're used to going on site, looking at drawings around a table, but on the screen, we're able to mark things up and really talk through in detail and have everyone looking at the same thing. And I mentioned scope earlier or even sequence. It's very easy to solve problems with that virtual environment, so that kind of helped. But now in terms of when things are actually built and we find like gaps, things that we're missing that we just didn't know about, I do agree that there are some challenges with that, but a lot of us kept working the whole time. So whether it be photos or on-site meetings, we find a way to work it through, and if we need to ask questions about the design to make those little adjustments to make sure the detail is successful.
Yeah, and we had a couple of video calls from contractors during COVID pointing their iPhone at something, being like, why is there a hole
exactly.
here?
What do we do about this hole?
Kind of moving on to some of the bigger projects we've been working on. Josh, you guys are the developer for the one on Bloor Street. That's 100% custom fabricated, custom designed facade with Foster's. Have you seen any kind of encouragement from the city, from jurisdictions to actually take that leap and do something of high quality, of high performance?
So I think the Toronto Green Standard is a good place to start. It has its downfalls, it's not perfect, but it is nice to have something aspirational and predictable. And one of the things Yelena said that I think is really important is that all the stakeholders know what is, what's coming, and what's to be, so we can plan our procurement and our kind of supply chain process around it. And I think that's really important. And what I'd like to see going forward from the city is a bit more industry involvement, whether it's from the consulting discipline side, whether it's from the architectural side, from the GC side. There are technology is moving faster than a 5, 10, or 15-year plan can predict. So there are things coming online that could be considered, and that's where elements like LEED and even something like WELL that's just come out, or rather come to the forefront now in reaction to the pandemic. We need a bit more dialogue between the two to make it even better, and I think that's a process that could continue going on and be iterative.
Yeah, it's an interesting point, because once, on the design side, and then you have sometimes 5 years to execution, technology has moved on a huge amount by then. So it's very, very difficult to plan ahead for that kind of stuff. Like, is your facade system going to totally change by the time you actually come to execute it?
And that, in terms of city support, the one specifically, which was originally proposed in 2015, designed in 2014, we had a desire from the city to achieve a higher level of the Toronto Green Standard than was required, and that was on balance for the density we were asking for. So we did actually a study just earlier this year where we are actually we're exceeding the current required green standard of today, even though the project was designed 8 years ago, which speaks a lot to the abilities of our consultants to design for the future, if given the pathway to do so.
Given what the parameters are going to be. All of that, I mean, you had trades on very, very early. Yelena, you deal with this a lot. Are you seeing any resistance from designers, from trades, even from developers to get involved super early? I know everyone, especially on the design side, can be a little, don't touch it, it's mine. during the process. So how are you seeing that people react to that?
No, I definitely understand the don't touch it sentiment, but in reality, like a lot of these projects, and even some of the ones we've seen today, they're so complicated. There's no way to achieve them without some sort of collaborative process very early in the design where everyone's at the table. And for a lot of the projects that Comtel has done with complicated facades, it's typically delivered through the design assist model. And what this design assist type of model allows for is exactly that early collaboration. And the big benefit for a lot of us is also the cost certainty you can achieve. And then ultimately, from our end, we get to start planning the job a lot earlier, which affords a lot of benefits on site. And just to speak a bit about more of these benefits on the cost end, the end goal of this design assist process is to hit a guaranteed maximum price, a GMP that we can trust. And you can't achieve that with other contract types. And what's really important here is that partnership between the design team and the facade subcontractor. And they're experts in their own supply chain, and they have the resources in place to lock in prices early, order things early, and hedge against the cost escalation risk that can come up, and as we've seen in COVID, and also be able to feed in their expertise on their supply chain to the design and actually advise on what's achievable without going past the budget. And then another piece, and you mentioned TGS, Josh, like these performance targets, they keep getting higher and higher, and unless you're talking about these things early on in the design, you're not procuring the material necessary to hit those, whether it be R values or tightness requirements and what have you. So that's also been a very key thing for us. And then again, on planning, we're able to get in early and figure out how to actually plan the job schedule, any other engineering that might be required. And it really helps deliver a better system and really minimizes the risk on site when it comes to both cost and field installation.
Given the people in the room, I don't think you're saying anything controversial there for sure.
No.
Josh, you went for 100% custom pre-design for one block. What did you really see in that process? How did it pan out, and especially over the time frame that you had to do it?
So when you're looking at pretty innovative and challenging design, it was important to do it that way. We obviously start with design through our design architect, which was Foster's, and then we worked with CORE locally to coordinate and work to the Toronto standards. From there, ran through cross-coordination in excess of 15 different consulting groups to go through and work every single detail through. It was a very important element for us to have the design as developed as possible when it came time to engage with trades. So then you engage with the trade, or rather you engage with the industry to start, doing a long, kind of more drawn-out RFQ process, narrow it down, and then when we engage with the trade, then comes their initial drawings and starting to have them interface with the team. And you now have a trade who's coming to engage with a team that's been together for 4 years already.
Yeah.
So we're all walking lockstep in a certain way, and it's bringing that trade on board to how we're seeing things and bringing in their innovation and their expertise to develop it. From there, we went to visual and performance mock-ups, 6 separate visual mock-ups for different elements of the building. There's some very specific architectural details that Foster's is particular about. It's why their buildings look like they do. So there's a very high level of detail-orientedness that is just a necessary challenge when working with architects like that. From there, there are certain elements specific that weren't typical to the Toronto industry. We had large overhanging double-story panels. We had a whole bunch of very specific things that we needed to prove out, which we did. And we're really happy with the experience we gained and moving through that.
I know you're off to Europe tomorrow to see some of the mock-ups. How important has it been to get everyone in one place around a mock-up and actually see how it's working?
We had a mock-up booked, and we're ready to go in the middle of the global lockdown. In a country that treated it as harshly as any. So we've had to work with our trade together with our consultants to figure out, we had to engage a separate consultant who had an office in that locale, so we didn't have to worry about people in and out. Like Foster's luckily is global, and they have offices all over, and they have partnerships in pretty much every major city. So that's been a challenge. I think that we're going to get to it a bit later, but how that starts to change our perspective on, we had this very efficient, tightly ordered global supply chain system, and it worked very well for, it was quite durable for a period of time. But the efficiency that we found, or the efficiency that evolved in it, is a direct result of predictability. And when you throw a wrench into the machine, the whole thing potentially gets reimagined.
Speaking of wrenches in the machine, Anik, you've been doing a lot of this design assist type work and also getting called in when things haven't gone as they were supposed to. What kind of problems are you seeing, or what kind of things have you been seeing that you've been called in to fix? Like, it's surely a real challenge when that process hasn't been followed and you kind of thrown in at the last minute.
Right, so yeah, we've been talking a lot about design assist, and there are many, many good reasons to do it, and we've heard about those all day and from my friends here too. But there are some cons, believe it or not. So one of them would be that when you bring a contractor on board early, they're going to be bringing their own experience to the table, and so you're kind of you may be limited to that experience. There may be other solutions that could be better that the contractor's not comfortable taking on because it's different from his previous approaches. Another aspect worth considering is the contractor's supply chain. So, he may be used to working with, maybe 2 or 3 different suppliers, and if you need something different for this project, but, he's not ready to go beyond his supply chain, then that can actually cause problems, and we've seen that on project sites, even for simple components like gaskets, or things like that. So those are 2 examples, and that could lead to a reduction in innovation, or a reduction in quality on site compared to what was desired by the design architect. So a couple of examples on the same project. So we're working on a project in the southeast US where it's basically 8 stories of a parking garage with the office tower above. The parking garage spaces, if you can imagine, the design architect originally planned to have glass spandrels concealing the slab bands, but the remainder of what would typically be a vision area was basically open, so open parking space, right? Open to the outside. And then in front of all of it, vision and spandrel, the architect had planned to have fins as an architectural feature. Now, this was all designed and planned, and it went into the bid documents for the design assist contractor, and the contractor that won the bid had priced something different, and what he had figured was that it would be far more cost-effective to add vertical mullions at the vision areas, which is not something the design architect wanted. They had a different vision in terms of aesthetics. So because the contractor was not willing to modify his design and had priced it a certain way, the design team had to basically accept that solution. Another example related to the same job is that these fins at the bottom of the building twisted, if you can imagine. And so in the final product was not quite as aesthetically acceptable as the architect had wanted in terms of tolerances of the twist. But because that particular contractor had one supplier that he was working with to supply, and he wasn't able to get the tolerances that the design architect wanted, a compromise had to be achieved, which was not, perhaps ideal if the supply chain was wider. So those are 2 examples. Yeah.
That's something we see a lot, actually, when we put the design documents together and it goes to bid and someone bids it on a completely different system, and then kind of gets surprised a little bit when it comes in. what's the best way of dealing with that? And that's kind of an open question to anyone, but one of us works for a contractor.
I guess it's on me. No, I'm really glad you shared that with us and everyone in the room. Like in a perfect world, you would get the A-team on every project, and they'd be able to have the capacity to look far and wide for alternative solutions, or they would have been able to flag things like the tolerance of the fins early on. But in reality, or at least what I'm seeing, is that everyone is so busy, and when we're at capacity in terms of availability of various contractors, whether they be in facades or other areas, you may not always get the partner that you wanted. So for that, I would reiterate again that it has to be an early discussion, and then a compromise of like setting out, okay, we can't achieve this, however, we will do these 3 options, and then putting those on the table with the hope that there will be an approval from you, and then on the design side, and I know it's not always a win-win, but it's the aim is to find a compromise, like you said, and
yeah, so some good
manage that.
transparency early on, and not think you can sneak it through.
No, exactly. Exactly.
Talking about the kind of quality of designer stuff, Josh, you guys are doing some incredible kind of boundary pushing projects that we don't often or don't always see in Toronto. Are you actually seeing the market now maturing and wanting those kind of projects, or that kind of finish on the building?
Yeah, I think we're seeing a really different type of demand from clientele in the market. I'd say 20 years ago, the condos being built, when we shifted away from stone-based buildings and moved into typical window wall, there was an era of very typical building where you can kind of point them out when you see them around the city. It's that blue-green box everyone outside the industry tends to complain about. What I think people lack in their understanding is that that's what you can afford when you're selling condos at a certain price. The purchaser is demanding the maximum square foot they could afford, and they care less about what's on the outside. It needs to pass, they need to keep them warm, keep them cool, and that's about it. And I think that starting in mid-rise, we started to see a purchaser that's willing to spend quite a bit more to live in an iconic building on the outside. They cared about what their building looked like in addition to their square feet on the inside and then location. That in the last probably 10 years, but specifically in the last 5, has gone just exponentially strong in Toronto as we see these really innovative cutting-edge designs, which I believe would feel at home in the New Yorks, Tokyos, Bangkoks of the world, where years ago we'd look at those cities and say, why can't we have them here? There's Toronto architects, I'm sure in this room all around, that designed some of those buildings, that are saying, we're doing this all around the world, why can't we have this here? And we finally do. And I think it's a pretty special moment in Toronto when you see 4 times a year, 5 times a year, a global leading architect with a very innovative, creative design coming out, presenting a building, and the fanfare from the city around it, good, bad, and ugly. It seems as if what you want is a diversity of response.
Yeah, it's interesting as well, because what we've found doing projects of that scale and that quality is that they're approved more quickly. The local neighborhoods on board, the councils are generally on board, and they're selling more quickly too. So it's kind of a win-win from a development point of view. But as a team, we're all having to work a bit harder to pull that kind of stuff off.
So it galvanizes a base of people that otherwise wouldn't come out to support a typical building. So
it's very true.
You get a lot of outreach from the community saying, I want that in my community.
Yeah. So pulling off these kind of high quality facades takes a lot of new technology, and the couple of the speakers before us showed some of that really incredible stuff. Are we seeing that kind of technology from the trades being executed in Toronto, or is that still being done from elsewhere?
For sure. So today we definitely saw a lot of interesting technology that's coming up and whatnot. For Toronto, and kind of what I think will be coming up is not so much changing the technology, but actually introducing it in like a large format or more modular format. And it's very similar to unitized curtain wall that's already doing that. But as we start increasing these thermal performance requirements, it won't be glass towers anymore, and you'll have to introduce more opaqueness to the wall assembly. So my colleagues at Elliston have been looking at this quite a lot, and in a lot of other markets, they're seeing that curtain wall and window wall is being replaced completely with these types of large format panels or modularized panels. And even in Canada, there are a number of players that are developing their own systems that are borrowing from existing unitized technology or taking just steel studs and creating these larger panels that will help not only achieve better wall systems, but also expedite schedule and a couple of other benefits. And I think what's the most attractive thing for me and as a CM or GC role is the risk that ends up getting grouped or aggregated into that one party that delivers these panels. And I think that'll help a lot in terms of getting a better quality product that's installed a lot more reliably. And with that, of course, there are other considerations with logistics and how large they are and how they're shipped to site and how you can actually bring them up the building and whether or not you have to use a tower crane, which has a very precious schedule. So it is a more holistic conversation between performance, design goals, and then also actual construction, how you actually deliver the project with these newer approaches.
So kind of a lot more mixed, large-scale mixed material installation rather than just the unitized curtain wall that we're used to seeing. When you do something like that, when you're going to mix glass and cladding and solid panel and et cetera, to create an interesting facade, that's really putting all of your eggs in one basket from a risk point of view. And I know we talked about this a little bit before, Josh, but if you do that, if you hire one trade that has subs under them, or if you rely on one person to execute the facade, what does that do to your risk profile? And especially right now when we're seeing longer times for shipping, more expensive shipping, fuel costs going up, like, is that a good thing that you've got just one person to deal with, or are you starting to get a little bit scared?
I think that overall it definitely has a net benefit. Having that one kind of top of the pyramid trade that's responsible for the performance of an envelope eliminates a lot of that crosstalk where the aluminum guy says it's him, the glass guy says it's him, the caulking guy says that, and that kind of crosstalk gets eliminated. At the same time, there is risk. So while you get greater certainty and greater ability to act on schedule, quality, performance, that does come from some risk. And I think that really requires, we're in a unique position because we're both the developer and the general contractor. So we operate kind of hand in glove with our trade with as open and transparent a relationship as we can have to look at their subs, work with them at the time where the team was being put together for the subs. To have that transparent relationship was very important. And to build that confidence day-to-day, weekly, multi-time-a-week meetings to get through this process, knowing that there's a huge amount of work to be done before the first panel of glass gets put on the building. And that's important.
What kind of impacts are you seeing, though, as supply chain issues happen, or as, the last week we've seen a huge fluctuation in the market of not just the stock market, in the market prices of aluminium, of steel. What impact is that having on the projects?
So I think that there's an interesting thing that's happening kind of concurrently, which is you have, as we spoke about earlier, this kind of finely tuned global supply plan. And everyone had their plans and their procurement in order, and then we were hit kind of upside the head and turned everything upside down. And we've had to work with that trade to figure out how to do it. We were fortunate that the trade we have has a North American facility. So we were able to make the decision to produce here locally, still with some supply abroad, when we could move that material, move it quickly, move it efficiently, produce it here, and be able to, at various points through our production and installation, reevaluate. Yeah. So really, I think everything in this world bears risk. Crossing the road bears risk. What matters is the partner you have and the willingness to work together to solve those problems as they arise, and determine the best path when there are forks in the road.
Yeah, absolutely. And we've seen projects switching materials, switching structural systems, and all that kind of stuff over the last few months. So having a little bit of flexibility and the right team that's just going to roll up their sleeves and jump in, I guess, is kind of critical to success there. You said about kind of moving production to North America, and I know there's kind of trades from all over the world in the room here. Are we actually being able to see North American production, North American installers pull this off, or are we bringing in a lot of people still? We did the whole Renfrew facade reclad last year, and we actually had to bring in trades from Germany to demonstrate how the system went together. and then have the Canadian team build it. So are you still seeing that, or are we starting to move more heavily into North American production?
I think it's creating this hybrid model that now there is a coefficient of risk that's assigned to that global procurement that has a value, both in raw dollars as well as cost. And with that, some slightly more expensive local options may present themselves as actually being the right net option to use. I think it will be not one or the other, but the hybrid mix of both. And people, the industry, need to be much more open to, I think, things that historically had been ruled out as not cost effective, that can now be when you consider all the factors.
So it's really thinking about value, not just cost, right? Not just bottom line cost. Kind of open it up to everyone else as well. What are you seeing? You know, what are you seeing people doing, and the quality of execution that we're getting now?
Well, I think in the sort of high performance facade world, because of, and Joshua alluded to it, because of the supply chain issues and the risk factors, a lot of what we're seeing, certainly, I suppose, if I refer to Passive House, there's a lot of local manufacturers that are having their products certified and getting them ready for those high performance projects. And so, you know, where there's a rapid schedule on a project, we're able to reach out to the local manufacturer and say, okay, can you get product to us in this short space of time? Equally, we're reaching out overseas, but we're finding more and more that the Canadian manufacturers and the North American manufacturers are responding with the right product and responding, you know, with the right schedule as well, which is really one of the most important factors, and that is actually leading to, you know, cost savings in overall terms. There's a lot of risk removed through that process.
Yeah, it's interesting. You know, the last year, the amount of projects that we've had to tweak design on or redesign slightly because someone's like, oh, by the way, the windows are 60 weeks out. And you're like, cool, the construction schedule was 48 weeks, but okay. Yeah. Is there any way around that? You know, what are you seeing on the construction and the facade engineering side? Is there the flexibility to switch systems to something that's local to hit timelines? I know that we're all kind of under pressure on fees and on development costs to make sure that schedule isn't impacted.
Yeah, I think on one of the projects I'm working with, they're using the IDP model in terms of delivery and procurement, and that's working very, very well. The glazing contractor was on board from the very, very, very start, working with the design team, working with ourselves to iron out the details, and the impact on schedule and cost is phenomenal. So for a project of that size, to have it ready for construction in such a short time frame is amazing. It's a bit of a different design assist process, but it definitely it's working for that project very, very well. So I think that's one way to address the potential problem.
What about on the construction side? Are you because you bear the cost risk a lot of the time for not being able to move things forwards. What are you seeing there? Like, what innovative solutions are you coming up with to make sure things get done on time?
I think there's a couple of ways to go about it. One story I can think of, and it's unrelated to COVID and all these schedule impacts to COVID, but a lot of the times in these DA formats, or is it whether it's IDP, and you are using a type of facade system that is prefabricated in a plant, like such as curtain wall, you can actually do the design early and then produce everything and then store it away, and then when the project's ready and then all the other hiccups were cleared, then the panels can come up and be installed.
That requires kind of real accuracy in the construction and development, which is interesting because, I feel like on the design side we've been pushing for that for a long time, but now it has a developer and contractor benefit too, which is kind of nice.
And I will say one more point, just thinking about this question, if I was in that situation where things had to change, is you might have to change the expectation of if you're doing like a bespoke custom system, and then you might have to ask for a more off-the-shelf system that the given manufacturer has readily available. And that could happen too, that switch. You could even borrow from a different project an existing system, and that will really cut the time necessary to get those panels on site.
Yeah, there's nothing I hate more than using something off the shelf. It's just,
Oh, is that a bad word here?
No.
Sorry.
I'm joking. It's just we always seem to end up being like, that's not quite right. What if we just change it completely?
Switch up the
So,
colors.
yeah. We've talked a lot about risk and technology and pushing the boundaries to make sure that the quality of the project is there. We're coming out of a period of extreme change into what appears to be another one with what's happening in the market and in the world right now. If you were kind of to look forward a year and we're all sat back on this stage, what's going to be the hot topic of discussion? What's the new tech? What's the new risk? What are people going to be doing?
I think we're going to be doing exactly what we're doing now, and what we were doing last year. I think that we're on a progression, and we're on a path that will continue to evolve. And while a lot of these market forces seem radical, and they are, we're locked down for 2 years. We've seen in all likelihood, a decade of Dow gains erased. We'll have a lost decade of economic output. I think that the engineers, the architects, and the people that want to build great things will always be there, and they will find ways to do it. And if it means that a project needs to be tweaked, it needs to be put on the shelf for a few years to be able to be done, I think that will still exist. I think we will continue to be pushing the boundaries of what we can do, because that's just in our human nature.
So you're thinking kind of incremental change over the next year. There's no like big shock coming.
I don't want to eat my words, but I don't believe so.
Yeah. What about you?
Well, I think for us, what we're seeing is that clients are coming through the door with sustainable goals in mind. They understand that net zero carbon is really on its way, and it's being rationalized into a set of guidelines that can really be followed now. Passive House has been there for quite a few years. There's a lot of processes out there, the message is out there now, and so when the clients are coming through the door, at this point, they're getting engaged in that sustainability discussion. And also there's enough of an understanding from a client that's going to continue to own the building. There's enough of an understanding out there at the moment as well that they get more longevity and less maintenance cycles and a more durable building. And then if they look down the road in terms of ownership of that building, it's long-term savings. And with the products that exist on the market now, what was perceived to be sort of a long payback time is much shorter now. For those sustainable efforts.
It's interesting because I do a lot of mass timber projects and getting towards doing a lot of net zero projects too. And I feel like the discussion has changed. It used to be us kind of pushing it on people and saying, you should really do this. Almost every mid-rise project that's come to us in the last year has been, maybe we could do this in timber. And that's like completely different even to a year ago. It has its own challenges, but it's definitely a different conversation now with a lot of developers, where they have goals, they have targets set on the money they're borrowing as well, that they have to achieve these things.
At times it wasn't, it wasn't even a discussion topic some years ago. It was us in the background just sneaking in better details. And, but now it's front and center. So I think, and that's driving kind of in large part the technology that's being designed for facade solutions as well.
How about you guys? Anik, maybe go first. What do you think is going to change? Is it a slow progression? What's going to be different? What's going to keep you up at night in 6 months' time trying to figure it out?
Keep me up at night, I don't know, but I think the answer is, for me, it's energy efficiency, because, I mean, you're talking about things staying as they are, but the one is kind of exceptional, right? You stated that it's achieving tomorrow's targets today, which is wonderful, but not the norm, I think, right? So as energy codes become more and more strict, you're not going to be able to rely just on the mechanical systems to achieve the whole building energy performance. The envelope is going to have to get better. The details are going to have to get better for everybody, not just the passive house construction or those that are aiming higher. And that's the big. I think for me, if I were to have one takeaway, this is it. Like, details have to get better. The design of the opaque assemblies must be better. So understanding, like, okay, we're maybe not used to using, for example, intermittent clips to hang a metal panel, but everybody has to get on board, from the designer to the contractor on site installing these things. Everybody has to know what the options are, how to optimize it. There's not one solution, there's actually many solutions. Tons of manufacturers here in Canada offer it. It's out there. We just have to, adopt it, embrace it.
Yeah, it's an interesting point because a lot of the energy modeling we've been doing recently, just the air tightness gives us a 20% energy saving. It's nothing to do with how much insulation, triple glazed windows or whatever, just don't make it leak. And I always use this boat analogy. I'm like, you can have the most expensive boat in the world, with a hole in it, it's not a boat anymore. And we're kind of seeing the same with the quality of the facades that we're having to do. It can look pretty, but if there's gaps in it, if there's unresolved details, then it's not really doing its job.
Yeah, and just to add to that, you can have the best details in the world, but if it's not implemented, it's worth nothing. Just saying.
No, it's a really good point. And to what you were saying, Josh, if you guys are not going to see a lot of progression, it's probably because you were aiming at a TGS that was 5 years away. So
let me just clarify. When I said what we're going to see in the years today is the progression that we have seen, and that progression won't stop.
Yeah.
That we just, 2 years of lockdown, we saw massive changes to our industry. We saw massive changes to what people wanted to deliver. We saw great projects that were pushing boundaries at a time where everyone could present them virtually. So I just feel that there's that natural progression, regardless of whatever forces are going to get thrown at us.
Yeah, and it really feels like the bottom of the market is going to be lifted up more than the top is pushed up, to be honest. Like, I know most of the people in this room are probably not in the bottom end of the market here. We're here to talk about the quality of the products and services we offer. But to me, it has felt like the top end is doing well, and everyone else is going to have to come up to meet the energy standards to meet the quality the market's demanding as well. We're almost right up on time. Does anyone have any kind of final comments, or we could maybe possibly take a couple of questions from the room as well if anyone has any burning issues that they would like to see discussed? I don't see any hands up, so aha.
Hopefully we won't take a pile of time, I truly love the conversation we're having up here. And typically speaking, there's a great mindset on how to embrace technology at an architectural level, at a consulting level.
Now you've got the microphone.
Sorry.
Could you just repeat the bit about how you loved what we were talking about?
No, I do. I love what you were talking about. So I'll introduce myself. My name's Steve Newlong. I own and run a number of companies that are all related to building envelope, glazing, metal panel systems, structural steel, and in a variety of the great, cities here. We're doing work in major urban centers and trying to do very complex buildings, Toronto, New York, LA, San Francisco, and in a week, London, England. And when I'm listening to what you're going through, what jumps to mind for me is that there's a very big disconnect between where technology is and the whole construction process. It's got momentum in a very archaic way. So we're able to bring solutions to the table, and there's a number of other facade contractors here that are very capable on this front. And we kind of feel like the redheaded stepchild. So there's a nervousness at a GC level. And and the consultants and the architects represent, effectively the owner. But there's a reluctance to bring facade or building envelope contractors in early, because it means there's a commitment to them without knowing what the price is. And we'll watch job after job after job come in, and at a very technical level, the drawings will get done because it's not done on a design assist basis. But when it comes to us as a facade contractor, we'll go through and bleed all over them because the details actually can't be done on site, or they don't make sense, or there's different suppliers all over the world. But we're not invited into that process, or very, very rarely are we invited in, And so when you talked about what are some of the things that need to change going forward to manifest now the great technology that's coming forward, how does it actually get on site cost effectively and efficiently? It seems to be that the method of including physical facade contractors, including the GC, because they're obviously the general contractor, but where the expertise lies, and we seem to miss that.
Yeah, and it's a really good point, which is what guided the assembly of the panel today was to have representation from each of those groups. It's a really tough one, and we see designers push for it quite often. We see contractors push for it quite often. But you've got to get 4 or 5 parties together who are all going to agree to do it, and one's going to be worried about cost, one's going to be worried about something else. So getting over that hump to actually commit to it is difficult. What do you guys think? Like, what could we change in what we're doing that could actually mean that we could make that design assist or that early engagement happen more often, and not just on the great projects? Yeah.
Well, I think IPD as a contract type goes a long way towards getting all of the right people around the table, and the nature of the contract itself is has everyone kind of bought into the success of the project.
Yeah.
So that's one way, and it's a great contract type. But I've also been, through the CCDC 14 design, and the design assist protocols that go with that. And you mentioned CM earlier as well, where a GC has a great relationship with a number of trades that they can bring with them early to be part of the discussion. So it depends on the scale of the project, how detailed you get with that. But I think everyone sort of welcomes it. Everyone wants it to happen. Everyone's sort of on board with it, but it's just not happening often enough, is really it.
I think we're about to get the hook, because I'm being gestured at from the side of the stage. But I wanted to thank you all for joining me, and it's so great to see so many people in real life too.
Closing comments, and then you can end the panel.
Okay, perfect. We've got just a few minutes for closing comments, so thank you all. And what do you really want to see, or what's your final thoughts on today? Don't all jump in.
I think it's. I think it's been amazing to see just the diversity of presentations, and just how advanced kind of what we're doing kind of within our offices is tried and tested, and I feel like we're doing that tried and tested very well. It's amazing to see the experimentation that's out there and the innovation that's out there, and so I've quite enjoyed that. So.
Yeah, absolutely. And if there are people who have any follow-up questions or like to talk to us, come and find us at the end. We'll be loitering somewhere. So again, thank you all for coming, and thanks for putting this on. It's been very interesting.
Hello. Thanks everyone. That's a fantastic panel discussion.
Just sit down. Just sit down for a minute.
Yeah. No, I appreciate it in the fact that for the delivery of these new buildings that we need to do, it's the collaboration is the key. And delivery is also a key component. Operations is another one, like in the sense of the people that are actually running the buildings. So I think it's a whole other world to get those people to buy into it. So fantastic. Thanks again for all of our speakers today. Really enjoyed it. I said it was a fire hose. It was a lot of talks and a lot of things to summarize. So thanks again, and thanks to Zach.
Yes. A round of applause for John. He was excellent today. Thank you so much. Appreciate it. So as I mentioned in the morning, we have recorded this event, so we'll share the link with you next week along with the feedback form. Those who want to avail the OAA and AIA credits, there are forms outside at the registration desk. Please fill that up. For AIA, I think the credits will get credited automatically, and for OAA, we will give you a certificate which you will then need to use for self-evaluation. I hope you enjoyed today's event. This is our edition number 91, country number 30. It's been fabulous. I think I'll rate this in the top 5 events we have done globally. It's been fabulous. This response reminded me of Auckland, where we had a full hall almost at 9 a.m. It's difficult to get people to come in early, and we started the event on time. And I think given the whole day. We've almost ended it also on time, which is a record. We've had events which stretch almost an hour late. This is fabulous, just 10 minutes, which is way normal. So thank you all. A round of applause for all of you for coming out in person, still at a time when there's a lot of uncertainty. Really appreciate. This means a lot to us as an organizer and to our event sponsors. So thank you all for attending in person, and I hope to host you next time at the next Zach World of Facades in Toronto, or whichever part of the world it is. Thank you all. Thank you all. We'll have a photo session with the panelists, and those who want to come and take some photos, they can please come on stage. We'll take a photo with the panelists first. Can I have Shivani here, please? Thank you. If you have speakers from the day, if you'd like to come, Mr. Hamid, I see you. If you want to just come and join on stage, we'll take a couple of photos. Anybody else wants to take a photo with this lovely backdrop, please, you're more than welcome to come on stage. No, it's okay. I'll just call Hamid too. Hold on. Two more of us. Waiting for me. No. I didn't know. Right? Thank you. Thank you so much. Thank you. Thank you so much. No. Thanks for your support a lot. Always fabulous. Yeah, sure. Why not? Please. Yes. Since you saw her?
Yeah, and it was great. It was probably the best trip I had. It was phenomenal.
John,
fabulous.
I like what
Thank you so much. As always, you were amazing.
Excellent. Thank you. I'm glad that worked out. Okay.
John? Thank you. I have family, so I'm taking them out to the circus. Oh, you're taking them out? Yes. Thanks, man. So nice. We'll catch up on Monday. Yeah. Deal? Thank you.
I think we're doing Dallas. We're doing New York.
Yeah, New York's already booked. I don't think so Dallas is booked now. Yeah, right.
Next year we'll look at that.
Absolutely. Take care. See you. Okay, I'll give you the reference. Perfect. Yeah. Come on, anyway.